Calculate the limit as x approaches 1 of stuff. Whenever you're trying to find the limit algebraically, you just take that number, substitute it in for every x, and hope that nothing crazy happens. Now, I'll tell you what I mean by something crazy happening. That's not going to happen here. Okay, we can plug in 1 for x squared, so this will look like negative 1 squared over 2 plus, plug it in again, 2 times 1 plus 4. And then use the order of operations to simplify stuff. So negative 1 squared is 1, so we get a half, plus 2 times 1 is 2, plus 4. Negative 1/2 plus 2 is negative, just kidding, 1.5 plus 4, which is 5.5. Now, this is just a normal number, which means this is my answer. Now, if I were to have something like infinity over infinity or 0 over 0, that would be a problem for a later day, which I know you will see if you continue to watch my videos. But all we have to do is take care of that. That's it. Compute the limit as x approaches 1 from the right side of this whole thing right here. Now, there is an algebraic method that you can do this. If I were to plug in 1, that would give me my answer as long as this whole thing isn't undefined when I plug in 1. Well, I'll tell you what right now. If I plug in 1, I get 0 on top. I get 1 minus 2 plus 1, which is 0 on the bottom. I can't plug in 1. This is undefined at 1. So what I need to do is I need to graph this. Now, I'm going to use a graphing calculator and paste the graph of the picture right here now. Now, as you can see from the picture, the limit at 1 actually doesn't exist because the left side and the right side don't meet up. But what this plus sign is saying is, where is my limit headed as it approaches 1 from the right side? As you can see from the picture, once I hit 1, it kind of dips down to negative infinity and keeps going to negative infinity, which would make my answer negative infinity. Now, if this was a minus sign, that would mean from the left, that would be positive infinity. And if I were to put just regular 1 here, since the left and the right side don't meet up, the limit does not exist. But in this case, I only care about where my number is going, where this graph is going as it approaches 1 from the right, and it dips down, which means negative infinity is going to be my answer. Calculate the limit as x approaches infinity of negative 3x squared over 4x plus 4. Normally, when I calculate the limit algebraically, all I have to do is just plug in whatever number that is to x and hope for the best. Well, I can't do that. Not here. Not here because I have an infinity, and if I plug infinity, I get infinity over infinity, and that doesn't make sense. You're not allowed to do that. So what you're going to do, this little trick, is find out what the highest degree variable is on the bottom here. It's x. Take that x, put it over 1, like this, yeah, and put it over 1 again for the numerator. I'm going to multiply the numerator and the denominator by 1 over the highest degree variable. Why does this do that? Well, there's a little trick that says if you have, like, I don't know, some number over x and x is approaching infinity, x is going to get larger, 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 and eventually that'll turn into 0. Okay, so I can't have infinity over infinity, but I can have something different. So let's see what happens when I do that. I have the limit as x approaches infinity, right, of negative. I'm going to multiply 3x squared to 1 over x, which cancels out an x, so I get negative 3x over distributed property, 4x times 1 over x, the x's cancel out, giving me just 4, plus 4 times 1 over x, which is 4 over x. Now what I have is I can plug in infinity now. I have negative 3 times infinity over 4 plus 4 over infinity. 4 over infinity becomes 0. So this becomes negative infinity divided by 4, which is negative infinity. And so my answer, and if you wanted to double check this on a graphing calculator, you will see a type of line that kind of just dips down like that. This will head towards negative infinity. So when you get infinity over infinity, your decision is, well, which infinity is it going to? Where is it going first? Negative infinity is going to be my answer here. Tricky. Find the derivative using the limit definition. Oh, this one's going to be fun. The limit definition of the derivative is this. The limit as h, you might be thinking, what's h? You'll see. The limit as h approaches 0 of f of x plus h minus f of x all over h. This will give you the derivative. It's a mess, and there are shortcuts, but this is the problem that I created, so this is the problem that we're going to do. What I like to do is I like to take turns writing out what this is going to be, f of x plus h, and then kind of like plugging everything in, and magic will happen. But the first thing I need to do is find out what f of x plus h is. So to find f of x plus h, you need to rewrite this original equation. And remember, y and f of x, same exact thing. You're going to rewrite this equation, and you're going to replace every x value with x plus h. So f of x plus h is negative x plus h in parentheses squared plus 2 times x plus h in parentheses plus 1. So what I'm going to do is I'm going to write out that x plus h squared is a perfect square trinomial. I can FOIL this, split this and FOIL it, but I'm going to be a little lazy and just say that becomes x squared plus 2xh plus h squared. This is distributive property, so plus 2x plus 2h, and then plus 1. Distribute this negative, negative x squared minus 2xh minus h squared plus 2x plus 2h plus 1. Now, you might be thinking, oh, please let one of these guys cancel out. It won't, but don't you worry. It will, something eventually will cancel out. Now, what I'm going to do is I'm going to, over here, rewrite this guy, right? I already know that f of x plus h is this. So I'm going to write out the limit as h approaches 0 of f of x plus h, which is blah, 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 blah. So negative x squared minus 2xh minus h squared plus 2x plus 2h plus 1. Now I'm going to subtract f of x. I know what f of x is. It's that guy. So remember, when you subtract, and I'm going to skip a step, when you subtract a polynomial, you are distributing a negative. So when I subtract this green parentheses, flip the sign. So you become plus x squared, that's good news, minus 2x, that's good news, and minus 1, that's good news. Now you might be thinking, why? Remember how I mentioned magic before? Well, things are going to disappear. First, I need to put this all over h. Negative x squared and x squared cancel out. You should expect this to happen when you do problems like this. What else cancels out? 2x, negative 2x, positive 1, negative 1. So I now drop down the limit as h approaches 0 of negative 2xh minus h squared plus 2h. Now you might know from limits and computing limits algebraically that if I were to plug in 0 for h, and h, I would get 0 over 0, which is indeterminate, which is against the rules. But if I have an h in common with all of them, can I just factor out an h? I'll tell you, you can. So the limit as h approaches 0 of, let's pull out an h, negative 2x minus h plus 2 over h allows me to cancel out these h's. I missed. So the limit as h approaches 0 of negative 2x minus h plus 2 is going to turn that minus h into a 0, negative 2x minus 0 plus 2. And since I'm running out of room, I'm going to skip the minus 0 part and leave it at that. That is my answer. It's a mess. There are shortcuts for this, and I will have videos showing you the shortcuts, but this is using the derivative definition, the huge limit crazy thing right there. Always expect things to disappear. Always expect to factor out an h, and then your answer will be a whole lot friendlier once this whole mess is taken care of. Find the average rate of change over the given interval. So we have an equation, y equals x squared plus 2. We have an interval. I'm going to change that y into f of x just because it's the same thing, but I'm going to change it because I'm going to write out this formula right here. The average rate of change is the same thing as f of b minus f of a over b minus a if b and a are the endpoints of your interval. And you might look at that and say, well, that's a lot like slope. Yeah. Yes, it is, because rate of change is slope. So what I have to do before I even start this is I need to find out what f of b, or f of negative 3/2 is, and what f of a is. So f of b is going to be f of negative 3 over 2. And that's going to become negative 3 over 2 squared plus 2. Negative 3 over 2 times itself is 9 over 4 plus 2, which is, what is 9 over 4? 2 1/4. So 2 1/4 plus 2 is 4 1/4. 4.25. All right, so that's f of b. Let's get a different color and do f of a, which is negative 2. So f of negative 2 is equal to negative 2 squared plus 2. Negative 2 times itself is positive 4. Positive 4 plus 2. This math is a little bit easier, 6. So now that I know that information, f of b is f of negative 3 over 2. And f of negative 3 over 2 is 4.5. So f of b is 4.5. 4.25, apologies. Minus f of a is negative 2. F of negative 2 is 6. So 4.25 minus 6, all these colors, over b minus a is going to be negative 3 over 2 minus 2. So I'll just write that down in black. Negative 3 over 2 minus negative 2. 4.25 minus 6 is negative 1.75 over negative 3 over 2, double negative. So negative 3 over 2 plus 2 is 0.5. and that's positive. And negative 1.75 over 0.5 is negative 3.5, I think. Yeah. Negative. We got a negative one. So negative rate of change is decreasing, which makes sense because that's a parabola going down in this area. So I like it. I like it a lot. Fun. Find the value of a that makes the function continuous everywhere. So we have ourselves a piecewise function. That's a mess, but it's over t squared. It tells you that t can't be 0. Well, it makes sense because if you were to throw in 0 for this guy, you would get 0 squared on the bottom, which is 0, which means you get an undefined function, which is impossible. So what's going to happen is you're going to get a graph of this, and you're going to have a hole or an asymptote of some kind, or a breakage at 0. But I need to fill that 0 in. Now, I'm like, okay, well then find where things fall apart. Well, I can't just plug in 0 because it won't work. So what I need to do is I need to run to Desmos and make a graph. So I'm going to go to Desmos and do a graphing calculator. You could also do a regular graphing calculator, run to your own graphing calculator, but I'm going to graph this guy right here and see where my equation exists at 0. And then I'm going to paste that graph right there. All right, so if you take a look at my graph, and I zoomed in quite a bit, I typed this exact same thing into Desmos on my phone. I had to use X's instead of T's because that's all it gave me for the phone edition of Desmos. If I were to try to take my thumb, or if you're on a computer, take your mouse and hover over where X or T is 0, it'll say undefined. But if I get awfully close to 0, it'll tell me that T, or the Y value, is 0.25. So in order to fill that hole in, A has to be 0.25. Right now, I see this weird image that looks like that, but there's a hole there at 0.25. By allowing A to be 0.25, it fills that hole in. Now it's continuous everywhere. That's my answer. Find the derivative of y equals 5/4 x to the 2/3. If you're just finding the derivative of a polynomial and you have a bunch of, exponents, variables, coefficients here and there, that requires only the power rule. Now, this is what the power rule says. I'll just write out the definition. d dx means you take the derivative of, some constant, I'll call a, x to the n power. This is what I have here. A would be 5/4, x is x, n is that exponent right there. What you do is you take that n, you drop it down, you multiply it to the coefficient, keep x, and subtract 1 from n. That is the power rule. Again, bring the exponent down, multiply it to that, subtract 1 from there. So let's get rid of this. Okay, let's get rid of this now that I know that. What I'm going to do is y prime, or I could call it dy dx if I wanted to. I'm going to take that 2/3, I'm going to bring it down, multiply it to the 5/4 that's already there. X is x, and 2/3 I'm going to subtract 1 from. All right, so a lot of cleanup on this problem, but, that's fine. It's part of the job. 2 times 5 is 10. 3 times 4 is 12. I can simplify that. X to the 2/3 minus 1. That's the same thing as saying 2/3 minus 3/3 for those of you who hate fractions. All right, so let me clean all this stuff up a little bit. That gives me 10 over 12 is 5/6. X is x. 2/3 minus 3/3 is negative 1/3. So the way I will wrap this problem up, and I'll actually take 2 steps to wrap it up, is a negative exponent drops x to the other side of a fraction bar. Right now, it's on the invisible top of a fraction bar, even though, there's no fraction bar. I could put over 1 if I wanted to. Now I have it on the bottom. So 5 remains in the numerator, 6 in the denominator, x to the drop it down and make it positive 1/3. Now, you can leave it like that if you want to, but an exponent of 1/3 also gives you the cubed root, so this is the other way that we could write this out. Either of these is perfectly fine, either of these is simplified, and that's my guy. Y equals negative x squared. Find, this means the second derivative. So I'm going to take the derivative once. I'm going to take the derivative a second time and see what I get. So the first derivative, d regular y, d regular x, forces me to use the power rule. So the power rule is you take the exponent, you drop it in front of the x, or multiply it to whatever coefficient is there. My coefficient's -1, invisible 1, but -1. So I'll keep the negative there, drop the 2 down, the 2 in front, keep x the way it is, and subtract 1 from the exponent. So 2 minus 1 is 1. That's sloppy, so -2x. Now I have to take the second derivative, which means I take the derivative of that guy right there. So the way you write out the second derivative is d squared y dx squared. You could put, that would also mean second derivative, y double prime, but, whatever. Whenever I'm taking the derivative of a coefficient, forgot my word there, times x, just an x to the invisible 1, you just have the constant now. So if you're wondering, well, why? Well, pretend that's an invisible 1, multiply the 1 out in front, nothing changes, subtract 1 from 1, so x to the 0 is nothing, the x goes away. This is my answer right here. So the second derivative of negative, that's the worst looking circle I've ever made in my entire life. The second derivative of negative x squared is -2. That's it. All right, y equals -2x cubed minus 4x to the negative third. And my job is to find, oh my goodness, the third derivative. Whew. All right, I can do this. Dy dx means the first derivative. And I'm going to use the power rule not once but twice. The power rule means I take my exponent, multiply it to whatever coefficient I have here, and subtract 1 from the exponent. So take the 3, multiply it to -2, -6. Take 3 and subtract 1, and x to the third becomes x squared. But I got to do it again. -3 times -4 is +12. Interesting. X to the -3 minus 1 is -4. That's my first derivative. Now I have to take the derivative of that guy. So that's d squared y dx squared. I can write that out as y double prime if I want to, but I already wrote it out as that. Power rule again. Take 2, multiply it to -6 to gives me -12. Take x, leave it that way. 2 minus 1 is invisible 1, so I won't write 1 there. I know better. -4, multiply that to +12 to give you -48. X to the -4 minus 1 is -5. So that's my second derivative. I had to find the third derivative. Y triple prime. So -12 times x Okay, drop down. Oh, there is no, well, technically there's an invisible exponent, so multiply negative 12 times 1, you get negative 12. 1, invisible 1 minus 1 is x to the 0th, which means x goes away. So remember, if you're taking the derivative of blah, 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 x, the x just goes away and you're left with blah, blah, blah. Okay? Okay. Negative 5 brought down and multiplied to negative 48 is going to be positive 240, I think. I'm pretty sure that looks about right to me. X to the negative 5th. Subtract 1 from negative 5. That gives you negative 6. And let me clean this up a bit and say negative 12 plus... Whenever you have a negative exponent, move it to the other side of a fraction bar. You might be thinking, what fraction bar? Well, technically there's an over 1 here. So leave 240 on top, the numerator. Drop down x to the 6th on the bottom. That is your third derivative. The end, the answer, bada bing. Find the fourth derivative of y equals negative 5x to the 4th. All right. Well, this is going to use the power rule. Okay. Whenever you have, coefficient, exponent, variable, power rule. Okay. Don't overthink it. The first derivative, dy dx, is going to be take that 4, multiply it to negative 5, so negative 20. And subtract 1 from that 4, x to the 3rd. That's the power rule. Take your exponent, multiply it to your coefficient if you have one, otherwise bring it out front. And then 4 minus 1, exponent minus 1, there you have it. That's the first derivative. I have to go all the way to the fourth derivative. So d squared y dx squared is going to have me taking the derivative of that guy. Take 3, multiply it to negative 20, gives me negative 60. X to the 3 minus 1 is 2. That's my second derivative. Okay. In real life terms, that's acceleration. But you didn't ask. I just told you anyway. D cubed y, that's supposed to be a 3. It looks awful. Dx cubed is the third derivative. Take 2, multiply it to negative 60, so that's negative 120. X to the second minus 1 is going to be x to the invisible first. I'll leave it like that. That's called the jerk. You're a jerk. It's a dance. Look it up. It's great. Now I have to take my fourth and final derivative for this problem. So d to the 4th, y over dx to the 4th. Whenever I'm taking the derivative of something x, the x goes away. Why? Because that's an invisible 1. So if you take the 1 out front, it doesn't change to the negative 120 in any way. 1 minus 1 is 0, so x to the 0 is no more x. So there you have it. Fourth derivative. Find the derivative of y equals polynomial times another polynomial. Now there's two ways that I can do this. I can foil, well, not really foil, but foil this whole thing out, do power rule a bunch of times after I simplify everything. That wouldn't be the worst thing ever. But whenever you have something times something, a function times a function, you could use what's called the product rule. Now, the product rule is this. You call one of your functions u, and you call another one of your functions v, and the derivative of u times v is going to be u prime v, so the derivative of the first function times regular second function, plus v prime u. In other words, the derivative of the second function times the first function. Okay? So what I need to do is I already know what u is. I already know what v is. I'm going to go over here and I'm going to try to find out what u prime is and what v prime is. So u prime is going to be the derivative of this guy here. All right, I have a sum of powers, so I'm going to use the power rule once, twice, and 3 times for u prime. The power rule says that if you have a coefficient variable exponent, you take the exponent, multiply it to your coefficient, and subtract 1 from your exponent. In other words, 4 times -2 is -8. X is x. Subtract 1 from 4 and you get 3. So let's do it again. Bring down the 2. 2 times 5 is 10. X is x. Subtract 1 from 2 and you get invisible 1. The derivative of a number, just a constant, is always 0. So that's that. The derivative of 4 is nothing. I'm not going to write out anymore. So that's u prime. Now I need to find out what v prime is. V prime, again, is going to have me use the power rule 2 times. You take the number that's the exponent, multiply it to your coefficient, so 2 times -3 is -6. X is x. Subtract 1 from 2, so invisible 1. And then we have 2 here, which when I take the derivative of a constant is just like that guy, goes away. So now what I have is I have my u prime, there you are, I have my v, there you are, plus I have my v prime, there you are, and I have my u, there you are. So y prime is going to equal u prime, which I made green. Let me get my colors back. I'll put it in parentheses. U prime is -8x cubed plus 10x times v, which is -3x squared plus 2 plus v prime, which I got to be -3x, so let me get my red. I'm sorry, -6x, so -6x, not 3x, times u, which is -2x to the 4th plus 5x squared plus 4. Now, you know, if you're taking this for a college class, maybe you have a professor that's like, that's good enough for me, but no, I don't like it. It's too sloppy for good old Mr. Parrish. So what I'm going to do is I'm going to FOIL this guy out. I'm going to distribute that guy out, super combine like terms, get an answer, hopefully have enough space to do all that. -8x cubed times -3x squared is going to be +24x to the 5th. Okay, that's the F in FOIL. -8x cubed plus 2 is going to be minus 16x cubed. That's the O in FOIL. 10x, a very sugary term. 10x sugar. Look it up. 10x times -3x squared is going to be -30x cubed. Ooh, simplifying right there. Probably not the only thing, though, so I'm going to wait. And 10x times 2 is going to be 20x. This guy's just regular distributive property. Boom, boom, boom. Got to get that boom, boom, boom. Black Eyed Peas. Just hitting all the puns today. -6x and times -2x to the 4th is going to be 12x positive to the 5th. So that will combine with that when I get there. -6x times +5x squared is going to be -30x cubed. So another cube to combine with the other cubes that I got over there. And -6x, I already did the line, but I did it twice. -6x times 4 is going to be -24x. All right. Let's bring out a few more colors. Do I have anything with x to the 5th? Yes, I do. I have 24x to the 5th plus 12x to the 5th is going to be 36x to the 5th. There you go. Is there anything like -6x to the 3rd? Yep, minus 30x to the 3rd, which is -46x to the 3rd, minus another 36 or 30x to the 3rd. Any more x to the 3rds? Nope. So -16 minus 30 is -46. Minus 30 again is going to be -76. 10, 9, 8, 76 x cubed. That's a Philadelphia 76ers reference. Look that up. Again, punning very hard today. 20x, -4, or 24x is -4x. And there you have it. That's my y prime. Power rule. And again, what I could have done is I could have superfoiled that whole thing out, done power rule a bunch of times, but I didn't. Use product rule. And product rule is going to be very important. You're going to see that a lot, especially when you deal with trigonometric things. I'll have videos on that eventually. Find the derivative of y equals a polynomial divided by a polynomial. Well, if you have a polynomial divided by a polynomial, the best thing to do is use good old quotient rule. What's quotient rule? Well, you label the numerator u, you label the denominator v, and do u prime v minus v prime u over v squared. So we know what u is. We know what v is. We are going to find u prime and v squared. So u prime is going to be the derivative of this numerator. So the derivative of 4x to the third, power rule, multiply 3 times 4 is 12, subtract 1 from the exponent, x squared, minus multiply 2 to 3, which is 6. Turn that 2 into a 1 after you subtract 1, and that's u prime. V prime is going to be the derivative of the denominator. 4 times 5 is 20, so we got 20, subtract 1 from 5, that gives you 4. Minus 4's derivative becomes nothing, so that's nice. I also have to find v squared. Now, v squared is going to take this entire denominator and square it, which means it's not going to be this times this minus that times that. If you square it, you have to do perfect square trinomials. So that actually simplifies out to 4x to the 5th times itself, so 16x to the 10th. Multiply these two together and multiply it by 2. So 4x to the 5th times negative 4 is negative 16x to the 5th times 2 is negative 32x to the 5th. And then square that and you get 16. So let's find the derivative. Let's put it all together. Y prime. Y prime is going to equal u prime, which I said was 12x squared minus 6x times v, which is green, 4x to the 5th minus 4 minus v prime, which I made purple, so 20x to the 4th times u, which is red, so many colors, 4x cubed minus 3x squared, that's that. It's all going to be over 16x to the 10th minus 32x to the 5th plus 16. So let me FOIL this out and then distribute that and see if any magic happens, see if anything disappears. It's possible. I don't know. Maybe I could do some factoring. Maybe, maybe not. We'll see. 12x squared times 4x to the 5th is going to be 48x to the 7th. 12x squared times negative 4 is negative 48x squared. Negative 6x times positive 4x to the 5th is negative 32x to the 6th. Negative times a negative is a positive 24x. This distributes, so negative 20x to the 4th is going to give you negative 80x to the 7th when you multiply it by 4x cubed. And negative 20x to the 4th times negative 3x squared is going to be positive 60x to the 6th. All of that, all of it, still over 16x to the 10th minus 32x to the 5th plus 16. All right, so let's see if we can do some combining, and I'll bring it over here just in case there's more factoring going on. I'm not sure what my answer is going to be. I'll go standard form, biggest degree first, 48, x to the 7th minus 80. X to the 7th is going to be negative 32, x to the 7th. Let's get a different color out here. Negative 32, x to the 6th plus 60, x to the 6th. Is 28 x to the 6th. I have to think about that for a second there. That's supposed to be x to the 6th. What else? Nothing else combines. So negative 48x squared plus 24x. All right, I think I'm good. 16x to the 10th, oh my gosh, 16x to the 10th minus 32, x to the 5th plus 16. The only thing that I can do, and I'm running out of space here, so I'm going to do this all in my head. I can factor out a 4 up top, I can factor out an x up top. But if I factor out an x up top, that does mean nothing for the bottom. But if I factor a 4 out on top, and factor a 4 out on the bottom, all the 4s disappear. So what I'm going to do is I'm going to literally divide each and every one of these guys by 4. That'll get me my final answer. So negative 8, 7, x to the 7th plus 7, x to the ugly looking 6 that was, minus 12, x squared plus 6x. All over 4x to the 10th minus 8x to the 5th plus 4. Never said it would be pretty. I just said it would be fun. And that's quotient rule for you. Compute the derivative of stuff involving trig functions divided by stuff involving more trig functions. This is going to use the quotient rule. So I'll call you U and I'll call you V. And the quotient rule says, if I need to find the derivative of a quotient, do U prime V minus V prime U over V squared. So I have to find U prime V. So U prime first is going to be the derivative of that. The derivative of a sine is cosine. So cos x plus 1. On the bottom, I'm going to take the derivative of, I already used green, can't use it twice. Purple. V prime is going to be nothing plus the derivative of cosine x, which is negative sine x. V squared is going to involve me taking that guy and squaring it, which I'm going to write out as that and leave it that way because I have a feeling nothing special is going to happen if I were to FOIL it out. I would get 4 plus 4 cos x plus cos squared x. Nothing special is going to happen, I don't think. Not off the top of my head. Maybe I'm wrong, and we'll figure it out. All right, let's put this all together. So I have U prime, which is blue, cos x plus 1, that's U prime, times V, which is green, so 2 plus cos x minus V prime, so minus negative sine x is going to be plus sine x. See what I did there? Minus negative sine x is plus sine x. And then regular u, which I made red, that's going to be sine x plus x. All of that is going to be over 2 plus cos x squared. Let's do some foiling, see what happens. 2 cos x plus cos squared x plus 2 plus cos x plus sine squared x plus x sine x. Ugh, looks sloppy, but I fit it in. Fun fact, cos squared x plus sine squared x is 1. So after I put all of that over 2 plus cos x squared, I can say 2 cos x plus cos x, which is actually 3 cos x, plus cos x squared plus sine x squared, which is 1. So you guys cross out to become 1. 1 plus 2 is 3. Plus x sine x over 2 plus cos x, all of which is squared. And if I FOIL that out, I don't think anything special is going to happen. I think that's my answer. So yeah, quotient rule with trig functions. Very interesting. Find the derivative of f of x equals the fourth root of negative 3x to the fourth minus 2. So what we have here is we have a function within a function. So that's going to require the chain rule. Now, a lot of teachers might use like u's and v's and f's and g's, but I don't like to do that. This is how I like to view the chain rule for me. This is how it works in my little brain. I have an outside stuff and I have an inside stuff. What you're going to do is you're going to take the derivative of the outside stuff, okay, keep the inside, and multiply everything by the derivative of the inside stuff. Okay, so take the derivative. So first off, before I can even think about doing this, I need to rewrite it. F of x equals, instead of the fourth power, or the fourth root rather, I'm going to turn that into the 1/4. So there's my outside stuff. Okay, my inside stuff is negative 3x to the fourth minus 2. Okay, so the derivative, let me get some different colors going on here. The derivative using the chain rule is take the derivative of the outside stuff. So that 1/4 is going to come down. So you're pretending that this is like the to the 1/4 power. Bring down the 1/4, all right? Subtract 1 from that 1/4 gets you negative 3/4. And that's the derivative of the outside stuff. Keep the inside stuff. So negative 3x to the fourth minus 2 is going to stay there. But we're going to multiply everything by the derivative of the inside stuff. So the derivative of the inside stuff is going to be multiplying this to negative, or the derivative of negative 3x to the fourth, which is negative 12x to the third, minus 0. So let's clean this up. Let's clean it up. I have a fraction, okay? That's going to go to the bottom of a fraction, so let me write a big fraction. I have right now 1 on the top part of the fraction, the numerator. I'm not going to do anything yet. 4 appears to be on the bottom. Everything taken to a negative exponent is going to have me drop that down and make it 3x to the fourth minus 2, negative 3x to the fourth minus 2 to the positive exponent. Then this is technically over 1, so I'm going to write negative 12x to the third. And my last step is going to involve me cleaning this up. So I'm going to divide 12 from 4, bring the negative out front. So this becomes 3 over, and I'm going to put this back in root form because that's how it was given to me. So I'm going to say the fourth root of negative 3x to the fourth minus 2 cubed. Now, there's multiple ways that all of this could be written out. Multiple ways, but this is the way that I ended up with. So this is the way that I'm sticking with. The end. Just kidding, not the end. I forgot x to the third. Hee hee. The end. Find the derivative f of x equals sine 2x to the third. All right, so I have a trigonometric function, but instead of just having sine x, I have other stuff. So this is going to require the chain rule. All right, remember when you do the chain rule, there's 3 steps. You're going to take the derivative of the outside stuff. Okay, so outside stuff derivative, keep the inside stuff, but then multiply everything by the derivative of the inside stuff. So you might be looking at this and saying, all right, well, what's outside, what's inside? Well, that's inside, and the sign is outside. So the derivative of this using the chain rule is going to be the derivative of sine, which is going to be regular cosine. Keep the inside stuff, but multiply everything by the derivative of the inside stuff. So, which I should have put there. So that would be 2 times 3 is 6. X to the third becomes x squared. And just to clean it up a little bit, I'll bring it out front. 6x squared times cos 2x cubed. And that's my guy. That's my answer. Find the derivative of a polynomial times a trig function with an x squared in it. All right. So this is going to involve a combination of product rule. And then when I take the derivative of this guy, I'm going to use chain rule. So remember, product rule is u prime v plus v prime u. So let's set that all up. So this is regular u, this is regular v. I already said that. So it's right there. U prime is going to be, drop down to 5, 10 x to the fourth plus nothing. V prime is going to involve chain rule. The chain rule is take the derivative of the outside stuff, keep the inside stuff, but then multiply everything by the derivative of the inside stuff. So v prime is going to be the derivative of the outside, so the derivative of cosine, which is negative sine. Keep the inside, x squared, but multiply everything by the derivative of the inside. And the derivative of x squared is 2x. So cleaning this up, I get negative 2x sine x squared. So let's put this all together. Y prime is u prime, which I called 10x to the fourth, v, which is cos x squared, plus v prime, which was negative, so let's put that plus into a negative, minus 2x sine x squared times u, which was 2x to the fifth plus 3. I know I could distribute that, make that negative 4x to the 6th, negative 6x, and then, attach sine to it. But that really won't get me anywhere. Nothing's going to cancel out if I do that. I don't think it will. Nope. So I'm going to leave it like that. It looks kind of sloppy, but it's acceptable. So that's that. That's power rule or product rule and power rule and chain rule. So many rules. Where are we? School? Just kidding. Thanks for watching. Like and subscribe. Find the derivative of a polynomial divided by a trig function where the inside of the trig function is more than just x. So what we're going to have is we're going to have quotient rule. So I'll call u u. I'll call u v. And quotient rule is as follows. U prime v minus v prime u over v squared. So I have u, I have v, I have to find u prime, I have to find v prime, and I have to find v squared. So u prime, let's make that, I don't know, green. I haven't used green yet. U prime is going to be just, straight up power rule. Take that 2, multiply it to -2. That gives me 4. Drop that x squared down to an x to the first. -5 disappears when you take the derivative because it's a constant. Dunzo. Now, to find v prime, that involves me using chain rule. So chain rule is going to be the derivative of the outside, keep the inside, which I'm putting in parentheses, so this is the inside, but then multiply the whole thing by the derivative of the inside. So the derivative of the outside is going to be the derivative of cosine negative sine. Again, chain rule is the derivative of the outside, keep the inside, that's supposed to be a 2, keep the inside, but multiply everything by the derivative of the inside. So I'm going to multiply everything by, drop that 3 down, multiply it to 2, so 6. X to the third becomes x squared. So let's make that a little bit more presentable and throw that negative out front, the 6x squared out front as well, and then sine of 2x to the third. Now v squared, and I'll make that blue, I haven't used blue yet, except for over there. V squared is just, don't overthink it. When you have a cosine and you square it, you only square the cosine part. So v squared is going to be cosine squared of 2x to the third. That's it. Okay, so let's put it all together. Okay, u prime, which was green, u prime is going to be -4x times v, which was the original cos 2x to the third. So I'm writing that out carefully. Minus v prime, which was -6x squared sine 2x to the third. So double negative is going to make minus negative. So minus negative is plus 6x squared sine 2x to the third times u, which is this little polynomial right there. So I'll put that in parentheses. I'll actually put a nice little bracket. -2x squared minus 5. Close that up. All over cos squared 2x cubed. Now, I'm going to stop there because I guess what I could do is if I really, really, really wanted to go above and beyond, I can distribute that ugly mess right there, but it's not going to do me any good. It's not going to get me anywhere. It's not going to allow things to cross out, or no trig identity is going to pop out all of a sudden and help me out. I'm going to leave it like that. So that's what y prime is. Definitely not pretty, but that's it. Find the derivative of y equals ln of x cubed. Well, the derivative of ln of x is 1 over x, but this is an ln of x. This is ln of x cubed, which is going to require the chain rule. So let me throw that in parentheses. The chain rule is you take the derivative of the outside. So the derivative of ln of stuff is 1 over stuff. Keep the inside, so inside the parentheses is going to be x to the third, but multiply the whole thing by the derivative of the inside. The derivative of the inside has me dropping that 3 down and turning that x cubed into x squared. Now this simplifies, right? That could be moved to the denominator or the numerator, which is what I meant to say, over x to the third. And since x squared over x to the third simplifies, that leaves me with 3 over x. So in the end, and let me rewrite it out, Lincoln Park, in the end I have 3 over x. That is the derivative of ln of x cubed. Find the derivative of y equals e to the 2x cubed. Now the derivative of e to the x is e to the x, but this isn't e to the x. This is e to the 2x cubed. So this is going to require a chain rule. So I have an outside and I have an inside. It would be nice if I used the pen function. This is the inside. Okay, the derivative of chain rule, or in this case here, means you take the derivative of the outside. So y prime is going to be involve me taking the derivative of e, which is still e, keep the inside, so times 2x cubed, but multiply the whole thing by the derivative of the inside stuff. The derivative of the inside stuff is 2 times 3, which is 6. 6x squared, because that 3 becomes a 2. Let me reorganize this to make it look prettier. Let me move this out front. And I am left with 6x squared e to the 2x cubed. And that is my derivative. Find the derivative of y equals cosine of ln of 4x cubed. So that's cosine of ln of 4x cubed. Well, this is definitely going to involve chain rule, but it looks like it's going to be chain rule within chain rule. So lots of chains. No big deal. We start out with cosine of stuff. Okay, when you're taking the chain rule, you take the derivative of the outside, right? So the derivative of cosine is negative sine. Keep the inside, so ln of 4x cubed, and then multiply the whole thing by the derivative of the inside stuff. Now, the derivative of this inside stuff has me doing chain rule again. So multiply the whole thing by the derivative of the inside stuff. This is ln. The derivative of ln is 1 over stuff. So the derivative of this guy, chain rule again, is the derivative of the outside, 1 over stuff. Keep that stuff, 4x cubed, but then multiply everything by the derivative of the inside stuff. The derivative of 4x cubed is 12x squared. So not much changes over here. It's just not pretty. Negative sign of ln of 4x cubed. That's a cubed. This guy over here becomes 12x squared over 4x to the third, which simplifies to 12 over 4 is 3. X squared over x cubed is x. So I could put this all together as, get rid of that and make it that. That looks better. So let me put that together as 3 coming out in front of sine. So negative sine ln of 4x cubed, close it, all over x. Gross. Gross, gross, gross. Find the derivative of y equals e to the stuff squared. So I know what the derivative of e to the x is. It's e to the x. But this looks like chain rule, and it might even be chain rule twice. Now, what I could do is if I wanted to FOIL this out, I could, and it wouldn't be so bad. But now I'm just going to stick with the chain rule twice idea because I just want to. You can't make me. So this is the inside stuff. E is on the outside. Chain rule says take the derivative of the outside, which is e. Keep the inside, which is 4x to the third plus 5 squared, but multiply everything by the derivative of the inside stuff. So this is the inside stuff. All of that I have to take the derivative of. So I'm multiplying e to the blah, blah, blah by the derivative of this, which also requires chain rule. So now I'm doing chain rule for this whole guy right here. So this says take the derivative of the outside stuff, which has me dropping down a 2, turning that 2 into 1, keep the inside stuff, so 4x cubed plus 5, but then multiply the whole thing by the derivative of the inside stuff. The derivative of the inside stuff is 4x to the third, which means let's multiply 3 and 4, make it 12. Drop that x to the third down to an x squared, plus 5 goes away because it's a constant. So to clean this all up, I have e to the 4x cubed plus 5, all of which is squared. I'm going to take that 12x squared, multiply it to 2 here, make it 24x squared times 4x cubed plus 5, close it, bracket it, although those brackets aren't necessary. And that's my answer. So you're not looking at anything pretty. I mean, if you really want to, you could distribute that and then distribute the e, but nothing's going to simplify, nothing's going to go away. I'm going to leave it like that, and yeah, that's my answer. Given h of x equals f of x minus g of x, find h prime of 2. All right, well, this is just flat out saying if I take the derivative of h, and the derivative is some function minus another function, it's going to be the derivative of a function minus another function. This is basic rules. Now, h prime of 2 is going to be f prime of 2 minus g prime of 2. F prime of 2, is a half, minus g prime of 2 is 1. And so h prime of 2 is a half minus 1, which is negative a half. Oh, that was neat. I liked it. I liked it a lot. Ah, yes, implicit differentiation. So when you take the derivative using implicit differentiation, what you do is, since it's dy dx, you're taking the derivative with respect to x. Okay, so anytime you take anything that has an x attached to it, you just take the derivative. Anytime you take the derivative with something that's not an x attached to it, you take the derivative but attach dy dx to it. Okay, so find dy dx using implicit differentiation. I'm going to take the ddx of both sides, so 3x squared plus 3y squared equals the ddx of 2. The derivative of 3x squared with respect to x is going to be regular 6x, the regular old derivative just like we're used to. However, the derivative of 3y squared is similar, 6y, but since we're taking the derivative of y with respect to x, we attach dy dx. That's going to equal the derivative of a constant, which is 2. 0. I meant to say 0. Let the record reflect. I meant to say 0. Now what I have to do is I have to get dy dx all by itself. Well, dy dx isn't all by itself. I have 6y attached and 6x floating. So let's subtract 6x from both sides. That gives me 6y dy dx equals negative 6x. Dy dx still isn't all by itself. I have to divide both sides by 6y, do the same thing here, divide both sides by 6y, cross u out, and I'll put over here my final answer, that dy dx, which is all by itself, equals negative 6 over 6, which cancels out, x over y, which is x over y. And that's my answer. Find dy dx using implicit differentiation. All right, 3x squared plus 3 equals, ln of 5xy squared. Well, whenever you use implicit differentiation, you're basically going to rewrite what you were originally given. 3x squared plus 3 equals ln of 5xy squared in parentheses. You're going to rewrite it, and you're going to take the derivative with respect to x of both sides. Now, in an easy sense on the left side, what that means is if you have, an x value and you take the derivative of it, you just take the derivative as normal. Bring that 2 down, multiply it there. You get 2 times 3, which is 6. That 2 becomes a 1, so x to the first, and the 3 becomes 0. Easy peasy. Well, not so much here. This is asking me to take the derivative of ln of stuff. Now, ln of x, the derivative of that would be 1 over x, but ln of something that's not x requires the chain rule. So what I'm going to do is I'm going to take the derivative of ln, the derivative of the outside, which is 1 over, keep the stuff on the inside, so keep 5xy squared, but multiply everything by the derivative of the inside with respect to x. So let me move that over here. That's supposed to be a straight line. Didn't turn out that way. So what I have is I have 5xy squared. I'm taking the derivative of the inside with respect to x. Now what I'll do is I will use product rule. I will call you u. It's not supposed to sound like UU, but it's too late. And I will call U V. Okay, so I need to find out product rule, which is U prime V plus V prime U. So U prime is the derivative of 5x with respect to u, I'm sorry, with respect to x, which is just 5. Not bad. However, over here, I have to take the derivative of y squared. So v prime is the derivative of y squared 2y with respect to x, which means I attach dy dx. dy dx. So product rule putting it all together is going to be u prime v. So I could actually write that over here. U prime v, so 5 times y squared plus v prime u. So I'll actually write this out as 5x times 2y dy dx. V prime, you're just making sure I got everything, and I did. Let me clean this up a little bit because I have a feeling some simplifying is going to happen, and I'll probably have to get rid of all that stuff over there too. So 6x equals, this actually just goes on the top, the numerator. So 5y squared plus 10xy dy dx. dy, I keep doing that, dx, all over 5x y squared. Now what I have to do is I have to get dy dx all by itself. So what I'm going to do is I'm going to multiply both sides by 5xy squared, multiply both sides by 5xy squared. That'll allow me to get rid of this guy on the bottom. So I have 60 x squared y squared, did I say 60? 30 x squared y squared equals 5y squared plus 10xy dy dx. All right, let me remove this mess over here so I can finish out the problem. I'm going to subtract 5y squared from both sides. So 30 x squared y squared minus 5y squared equals 10 xy dy dx. Last but not least, divide both sides by 10 xy. Actually, not last but not least, but that's fine. Divide both sides by 10 xy. You all cancel out. That leaves me with 30 x squared y squared minus 5y squared over 10xy equals dy dx. So let me flip the dy dx to the left. What I notice is all three of these terms have a y in common and a 5 in common. So let me pull out and divide out a 5 and a y. So my final answer is going to be 6x squared y minus, divide out a 5 and a y from that, so that leaves me with y, over, divide a 5 and a y from that, 2x. And there you have it. Find the second derivative using implicit differentiation. All right, well, let's take the first derivative. Take the d dx of both sides. When you do implicit differentiation and you take the derivative with respect to x, you just take the derivative normally for many of these. However, I'm writing and talking at the same time. Right off the bat, I take the derivative of a y value. What you do is you still take the derivative, multiply that 2 to the 4, bring that 2 down to a 1, so invisible 1, 8y. But since we took the derivative of a y with respect to x, we have to attach a dy dx. That's going to equal, I'm jumping the gun here. Take the derivative of 2, gone. So that's going to equal the derivative of 3x squared, drop that down, that is 6 x to the first, and now I have to get dy dx all by itself. So divide both sides by 8y, divide both sides by 8y, and dy dx is now simplified out to 3x over 4y. Okay. Now, the derivative of this guy, all right, so the second derivative is going to be me taking the derivative of this guy right here with respect to x. So this is going to require quotient rule. So I'll call you u, I'll call you v, right? And so I need to find u prime, which is going to be 3. I need to find v prime, which is going to be 4 dy dx. And I need to find what v prime or v squared is, which is 16y squared. So chain rule, if you forgot, I'll write it up here, is u prime v minus v prime u all over v squared. So let's put it all together. The second derivative, so the second derivative with respect to x, is going to be u prime, so 3, times v, so times 4y, minus v prime, which is 4 dy dx, times u, which was 3x, over v squared, which is 16y squared. Now I know something. Okay, let's start simplifying things, but I know something else. Okay, 3 times 4y is 12y, no big deal. Minus 12x, but dy dx, I already know what that is. Dy dx, right here, is 3x over 4y. So I'm going to turn that into 3x over 4y. And that's all going to be over 16y squared. So I have 12y minus, let me see, what will that be? 12x makes 36x squared over 4y. So that is x squared over 4, 9x squared over y minus sign, all of that over 16y squared. So I can maybe do a little bit more. I can pull out a 3, but other than that, I mean, I'm pretty much set. It's not a pretty answer, but, you know, it wasn't a pretty problem. You're not expected to get love and joy when you deal with implicit differentiation twice, product rule, or in this case, not product rule, quotient rule. This is not pretty. It was a lot of fun, though. Find the derivative of the function at the given value. All right, so first let's find the derivative, and then after I find the derivative, I have to plug in 3, and that's what it's asking me to do. So in order for me to find the derivative, I want to use quotient rule. So let's call u u, let's call u v. I need to find out what u prime is. So u prime is going to be nothing. That's going to make life a little bit easier when I get there. V prime is going to be 2x, rather, plus nothing. And then I have v squared, which is going to equal x squared plus 5 squared. And I'm not going to FOIL that out unless I have to. Okay. Quotient rule is u prime v minus v prime u over v squared. So I'm going to put it all together. Y prime is u prime, so nothing, v, which is who cares, minus v prime, which is 2x, u, which is 20, over v squared, which is x squared plus 5, all of that squared. Now my job is to find out what the derivative is when x is 3. So I need to find y prime of 3, which you're useless is going to require me to plug in 3 for every x. So I have nothing minus 2 times 3 times 20. Okay, that's that chunk right there. All over 3 squared plus 5, all of that squared. So I have negative 6 times 20, so negative 120, over 9 plus 5, which is 14, 196. Divide that by 4, you get negative 30 over 196 is 49. Yeah, that's it. It doesn't simplify any further than that. So yeah, that's my answer. What this means is find the derivative means slope of the tangent line. So what this means is if I were to graph that guy right now and say, you know what, I wonder what the slope is at 3. There it is. Couldn't look at it and guess it, but that's what it is. Negative 30 over 49 is y prime 3. Fun, 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 fun. Find the derivative of the function at the given value. So I have to take the derivative of negative tan 2x, and then when I'm done that, plug in negative pi. All right. The derivative of tan is secant squared. All right. But this isn't tan. This is tan 2x. So this requires a chain rule. So the chain rule is you take the derivative of the outside stuff. So the derivative of negative tan of stuff is negative secant squared of stuff. Keep that stuff, but then multiply everything by the derivative of the inside stuff. So this ends up being negative 2 secant squared 2x. That's what y prime is. But I don't want y prime. I want y prime of negative pi. So I have to calculate negative 2 times secant squared of 2 times negative pi, or negative 2 pi. Fun fact, secant squared of negative 2 pi is 1. How did I do that so fast? I paused the video and typed it in. So when you multiply negative 2 to it, you get negative 2, which means, find the derivative. Derivative means slope. If you learn anything from calculus, is that derivative means slope. So if I were to go to negative pi, look at this graph, and wonder, I wonder what my slope is, it's negative 2. So that's how it's done. Take the derivative of y equals the inverse cosine of negative 5x to the third. Well, that's inside stuff, so I'm going to put parentheses there. First things first, the derivative of an inverse cosine, I'm going to write it up here, is negative 1 over the square root of 1 minus x squared. Now, that's if it's just the inverse cosine of x. This is the inverse cosine of stuff, which tells me I'm going to have to deal with a little bit of chain rule because the stuff is not just x, it's a little bit more. So what I'm going to do is I'm going to take the derivative using the chain rule, which is, chain rule in general is you take the derivative of the outside stuff first. So we're going to write out negative 1 over the square root of 1 minus, however, keep the inside stuff. So I'm going to keep, instead of x, I'm going to write out negative 5x cubed. So this is me keeping the inside stuff. Don't forget the squared. Let's make that a little bit bigger. But then you multiply everything by the derivative of the inside stuff. So the derivative of the inside stuff is going to be 3 times negative 15. Negative 5, which is negative 15. I'm jumping the gun in my head. Turn that x to the third into x squared. And then maybe my last step would be for me to take this guy, scooch it up here. I have a double negative going on, so maybe those negatives cancel out. So let's pretend that that negative wasn't there, make it a positive. 15x squared. On the bottom, I have the square root of 1 minus, and negative 5 times itself is 25. X to the third times itself is x to the sixth. Can't do much more than that, so that's going to be my answer. Pretty gross. Find the derivative of the inverse of 5x equals negative 4x cubed minus 4. All right, so what I need to do is find the inverse of that. What you do whenever you find the inverse, and right now what I'm going to do because it makes my life easier is I'm going to pretend that f of x is y. So I'm going to pretend that f of x is y. Whenever I'm finding the inverse, the first thing I need to do is I need to swap the x and the y and then solve for my new y. So this is me doing exactly that. In order to get y all by itself, you have to add 4, crosses out. Now I have x minus 4 equals negative 4y to the third. I'm going to divide everything by negative 4, so divide everything by negative 4, divide everything by negative 4, So I have negative 1/4 x plus 1 equals y to the third. Now I have to cube root both sides. Cube root both sides, and that gives me y equals, now watch how I know what's going to happen. If I'm going to have to take the derivative, that cube root doesn't do me any good. I'm going to put it as to the 1/3 power. I have negative 1/4 x plus 1 living in my parentheses, so that becomes that. Now I'm going to write that out as the inverse. Now that's not my answer. I just have to find the derivative of that. Now finding the derivative of this guy requires chain rules. So you have the inside stuff, which is there. You have the outside stuff, which is there. So the derivative of the inverse is going to have me taking the derivative of the outside. So bring that 1/3 out front. 1/3 minus 1 is going to be negative 2/3. Keep the inside, so negative 1/4 x plus 1, and then multiply everything by the derivative of the inside stuff. The derivative of negative 1/4 x is just negative 1/4. That's supposed to be the end of the parentheses, but something happened there. Plus 1, nothing. So let's clean this up a little bit. All right, I now have this big fraction where so far 1 is on top. 3 is going to be multiplied to negative 4, so let's make this whole thing negative. So 3 times 4 is 12. And then I have on the bottom, because I can move this down, negative 1/4 x plus 1 to the 2/3, leaving me with just 1 on top. And that's good enough an answer for me. I think that's acceptable. It looks kind of gross. I mean, if I really wanted to turn this into a cube root of that guy squared, I could. But you know what? I've had enough. I've had enough of that problem. And that problem's good enough for me. Find the slope of the tangent line at the given value. All right, so the slope of the tangent line means if I were to go at negative 2, which is here, right, put a dot there, what is the slope of that line right there? Well, it looks like it's positive. Maybe it's 1. Looks like it's 1-ish, but I don't know, and that's what I need to find out. The way you find the slope of a tangent line is you take the derivative and substitute that value for x. So y prime of this polynomial right here is 2x, because bring down the 2, that goes to 1, plus, just get rid of the x, and the 7 disappears. Now what I do is I plug in -2 for every x value. So 2 times -2 plus 6 is the same as -4 plus 6, which is 2. So the slope of the tangent line, I initially guessed it was going to be 1-ish, but maybe my picture should have been better. Maybe it should have been steeper, in which case that picture would match up with this guy right here. So the slope of the tangent line at -2 is +2. That's all I have to do for that guy. Take the derivative, plug in your x. Find the slope of the tangent line at the given value. All right, so in order to find the slope of the tangent line, derivative means slope. All right, so the slope of the tangent line requires me to take the derivative of this guy and then plug in -3 for x. Now, the derivative of regular ln of x is 1 over x, but this isn't regular ln of x. So this is going to require chain rule. So chain rule is you take the derivative of the outside stuff. So my outside stuff is -ln. So it's going to be -1 over stuff. You keep the inside stuff. So you take the derivative of the outside stuff, keep the inside stuff, but multiply everything by the derivative of the inside stuff. So I'm going to multiply everything by -1 because the derivative of -x is -1 and the derivative of 2 goes away. So basically the only thing that changes is -1 times this whole negative thing becomes one whole positive thing. So I have 1 over -x plus 2. Now to find the slope of the tangent line at x equals -3 requires me to find y prime of -3. So y prime of -3 is 1 over -3 plus 2, which is 1 over 5. That's my answer. Slope of the tangent line means take the derivative. Find the equation for the tangent line at a given point. All right, well, the slope of a tangent line is found by taking the derivative of a curve or whatever we're dealing with and plugging in the x value. So let me start out with that. Let me take the derivative, y prime. That's going to give me drop down the 3x squared minus, drop down the 2 times 2 is 4, regular x plus 2 goes away. Now I take my x value and I find out that y prime of 2 of that guy is going to be 3 times 2 squared minus 4 times 2. 3 times 2 squared is 3 times 4, 12, minus 4 times 2, which is 8, gives me 4. Okay? So my slope of the tangent line is 4. So m, and I'm going to put m tan for slope of the tangent line is 4. What I'm going to do is I'm going to use point slope form to write out the equation of a line with a slope of 4. Why am I using point slope form and not like, slope intercept? Well, I have a point, and that point is 2, 2. So I'm going to write out y minus y sub 1 equals m times the quantity x minus x sub 1. This is the point that I'm going to use, x sub 1, y sub 1. My slope is 4, so I have y minus y sub 1, which is 2, equals 4 times the quantity x minus x sub 1, which is 2. Now, what this looks like graphically, all right, is graphing something like this. Graphing a cubic is going to give me something that looks like this. At some point 2, 2, I have a tangent line where a slope is 4. So again, the way we find this tangent line's equation is we start out by taking the derivative, plugging in 2 for x, and that gives me a slope of the tangent line. Once I have a slope of the tangent line, I have also a point of a tangent line. Use that point, and I can use point slope. And if you want to do slope intercept, then distribute, add 2, you'll get 4x plus minus 6, minus 6. So it all works out in the end. Fun, fun, fun. Find where the tangent lines are horizontal. Well, lines are horizontal when the slope is 0. You can get the slope of a tangent line by taking y prime, the derivative. So in this case, I want when y prime is 0. So let's find out what y prime is. Y prime is going to be drop that 3 down, drop the 3 to x squared, minus 2 times 2, which I think is 4, and drop that squared down to a single x, and the 2 just goes away. Now what I need to do is I need to set that y prime equal to 0, so I'm going to bring that over here, and I'm going to factor that guy out, which only has me pulling out the x and nothing else. So I have 3x minus 4. If 0 equals something times something, you're going to use the zero product property, and you take each factor, set it equal to 0. So x is equal to 0, and 3x minus 4 is equal to 0. Add 4, and you get that. Divide by 3, and you get that. So this is the x value. These are the x values, rather, where my tangent line is horizontal. Now, I don't know exactly what these values are, but this is a cubic. Cubics look like this. Okay? Cubics look like that. So at the very tippy top is where you're going to get a horizontal tangent line. And at the very bottomy bottom is where you're going to get a horizontal tangent line. I know this happens at x equals 0. I know this happens at x equals 4/3. What I don't know is the y value. But I can find the y value by taking 0 and 4/3 and plugging it into the original equation. Not the derivative, the original equation, because that gives me the exact locations as to where these tangent lines are horizontal. So let's do the easy one first. Let's find out what y of 0 is, which means I'm going to take 0, plug it into the original equation. So 0 cubed minus 2 times 0 plus 2 is going to be 2. So that, like I said, that was the easy one. 2 minus 2 plus 2. When I plug 0 into the original equation, I get 2, bada bing. Now, not the fun one. When I plug 4/3 into the original equation, I'm going to get 4/3 cubed minus 2 times 4/3 squared plus 2. 4 times 4 times 4 is 64. 3 times 3 times 3 is 27. 4 times 4 is 16. Times negative 2 is negative 32. 3 times 3 is 9. Plus 2. Let's make all of these have denominators of 27 so that I can combine fractions without having to use a calculator. So nothing changes there. If I multiply the numerator and the denominator of this guy by 3, that gives me 96 over 27. And if I multiply this guy by 27 over 27, I get plus 54 over 27, and now I can combine all of these fractions. So let's do the positives first because, I like being positive. 64 plus 54 is 118. 118 minus 92 is 22 over 27. Just trying to do this all in my head, making sure I'm not making a mistake, and I think I'm okay. I think that's pretty good. Again, 64 plus 54 is 118. 118 minus 96. I'll take it. So by plugging in 4/3, I now have my 2 points. There they are. There they are. Let me rewrite them out in a color I haven't used yet. Where are these tangent lines horizontal? 0, 2. And 4/3, 22 over 27. There you have it. Now you know exactly. Now you know exactly what to do. Find the critical points of y equals stuff. All right, the way you find critical points is you take the derivative and then set that equal to 0. So let's take the derivative, y prime. Y prime is going to equal 3, drop it down, x, turn that into a 2, minus, drop the 2 down, make it a 22, x to the regular x, plus 39, and that's it. Now I have to set it equal to 0. So 0 equals, can't factor it out. Can't factor it out. But once I get to this point right here, I could use a good old friend called the quadratic formula. Maybe it does factor out. I mean, it doesn't factor out regularly. You probably can factor it out, like maybe using like 13s and 3s, but I don't know. I'm nervous and I'm not going to risk it. So I'm going to use the good old quadratic formula. X equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a. So x equals negative, so here's my a, negative 22 is my b, and 39 is my c. So x equals negative 22 makes that positive 22. See what I did there? Plus or minus the square root of negative 22 squared minus 4 times a, which is 3, times c, which is 39, all over 2 times a, which is going to be 6. Ugh. All right, well, that'll become regular 20. Let's just use Siri. 22 squared minus 4 times 3 times 39. Oh, no way. It's 16. By the way, I said 22 because I knew that would become positive anyway. Oh, how nice is that? All over 6. So when you split this up into 2, x is going to equal 22 plus or minus 4. So we'll do plus 4 over 6. And x equals 22 minus 4 over 6. 22 plus 4 is 26. 26 over 6 simplifies to 13 over 3. 22 minus 4 is 18. 18 over 6 is 3. So these are my two guys. My critical points are going to be 13 over 3 and 3. Now, for many problems, critical points might require you to find the y value, but for these, we're only going to find the x value. If you want to find the y value, you would just plug 13 over 3 into the original equation, plug 3 into the original equation. But this leads to a concept known as increase and decrease, looking for intervals of increase and decrease. And usually for problems like that, we don't really necessarily care about the y value. All right, so I'm going to leave it like that. I'm going to leave it like that. Find where the function is increasing or decreasing. All right, so this is what I'm going to do. I'm going to find where the derivative is positive, because when the derivative is positive, that's increasing. When the derivative is negative, that's decreasing. What I need to do first is I need to find my critical points. Why? Because the critical points tells me where my derivative is 0. Once I get zeros, I can kind of break it up into intervals and figure out which ones are positive, which ones are negative, take it from there. So I have to take the derivative of this guy. So negative, bring that 4 down, turn x to the 4th into x to the 3rd. Multiply that 2 to 3, x squared becomes x to the 1st, and the derivative of negative 3 is nothing. I don't know why it took me so long to figure that out. Now, in order to find the critical points, I need to set my derivative equal to 0. While I'm at it, I'm going to factor negative 2x out. Okay, because 2 is divisible by these guys, the negative because I don't like my leading coefficient being negative, and there's an x in common with both. So when I divide out a negative 2 from negative 4, I get 2. And when I take an x away from x cubed, I get x squared. When I divide a negative 2 from regular 6, I get negative 3, and that's it. Now, the zero product property says that if I have 0 equaling two numbers multiplied together, or two factors rather multiplied together, I take each factor, set it equal to 0. So I have negative 2x equal to 0, and I have 2x squared minus 3 equal to 0. Divide both sides by negative 2, and one of my critical points is 0. Easy enough. Let's add 3 to both sides. Divide by 2, and x squared equals 3 over 2. Now be very, very, very careful. I have to solve for x, and the way I do that is by taking the square root. Do not forget your positive or negative. It happens all the time. So two other critical points, not one, but two other critical points are going to be positive or negative 3 over 2. So 0, negative 3 over 2, and positive 3 over 2 are where my original function is going to have a slope of 0. So neither increasing nor decreasing. Now what I'm going to make next is something called a sign table or a sign graph or a sign chart. Now S-I-G-N, not S-I-N-E. Don't get excited. All right. I'm going to put my x values for critical points right here. The negative 3 over 2, 0, and square root of 3 over 2. Not negative, but negative square root of 3 over 2. I'm putting those there in order. What I'm going to do is I'm going to choose values in between these numbers, and bigger than and smaller than, and plug them into my derivative to see if those values give me an interval that's positive or negative. If it's positive, that tells me that everything between here and here, or everything between here and here, or everything there is positive or increasing. And if it's negative, decreasing. So I need to pick numbers that are not exactly these numbers. Now, if you're wondering, well, why can't you just pick these numbers? Well, if I take these numbers and plug them into the derivative, I get 0, which kind of defeats the purpose. The 0 tells me that that's where a change probably occurs in increasing to decreasing. So square root of 3 over 2 is like taking the square root of 1.5. So that's going to be bigger than 1, but not that big. So I can use 1 and negative 1 as potential numbers to plug in. I'll use 10 and negative 10 because why not exaggerate things? And I plug these into my derivatives. All right, so let's start out with negative 10. So y prime of negative 10 is going to be this guy right here, negative 4 times negative 10 cubed plus 6 times negative 10. Now, I'm not going to overthink this. I'm not even going to do any math. Negative 10 cubed is negative 1,000. You multiply that to negative 4 and you get 4,000. 4,000 minus 60 is going to be a huge number. But the most important thing is that it's going to be positive, which tells me that when I plug in negative 10, it's increasing. So this is why I call it a sign table or a sign chart, because by plugging in negative 10, I know everything from negative infinity to negative square root of 3 over 2 is going to be an increasing part of this function. Now, if you're like, well, that's easy, I'll just get negative, positive, negative. I don't know. Probably, but I don't know. So let's find out what y prime of negative 1 is. Okay, that's going to be negative 4 times negative 1 cubed plus 6 times negative 1. Negative 1 times itself 3 times is going to be negative 1. Negative 1 times negative 4 is positive 4. Positive 4 minus 6 is negative 2, which tells me that between negative square root of 3 over 2 and 0 is decreasing. Almost there. Y prime of regular 1 is going to be negative 4 times 1 to the third plus 6 times 1. 1 to the third is 1. Negative 4 times it is negative 4. Negative 4 plus 6 is positive. So that tells me that between 0 and root 3 over 2 is going to be an increasing function. Last but not least, let's plug in 10. 10 tells me what's happening after the square root of 3 over 2. So negative 4 times 1,000, or, well, 10 cubed, which becomes 1,000, plus 6 times 10 is going to be 1,000 times negative 4, which is negative 4,000. Negative 4,000 plus 60 is still going to be negative, so it stays negative. Boom. All right, now let's get rid of, I hate it, but we need to get rid of this to give ourselves some space. Okay? This is now telling me that everything is increasing. Everything is increasing on the intervals negative infinity to negative root 3 over 2. Also, it's increasing on the intervals 0 to root 3 over 2. And it's decreasing between negative root 3 over 2 to 0 and root 3 over 2 to infinity. So there you have it. Very busy problem. Lots to do. But without graphing, I was able to figure out where stuff is increasing and decreasing. Find all points of discontinuity. Discontinuity means if I were to graph this, where will my graph break? Maybe it becomes a hole, all right? Maybe it becomes an asymptote. Where does that stuff happen? Well, easiest answer is this stuff happens when my function is undefined. Where is a function undefined? When the part in the denominator is equal to 0. So let's find out when 4x plus 4 is equal to 0. Okay, minus 4, 4x equals negative 4, divide by 4, x equals negative 1. So my one and only point of discontinuity, also known as POD, not to be confused with a really good nu metal band from the early 2000s, late 1990s. I liked them. I've seen them live a few times. My one and only point of discontinuity is when x is -1. That's it. Also, a big shout out to POD, a very good band. Find inflection points and where the graph is concave up and concave down. All right, before I do anything, let me remind you, or let me teach you what's what. Inflection points are when what your x values are when your second derivative equals 0. Concave up on a graph is when you have parts of your graph curling up like that. That happens when your derivative is positive. Concave down, very similar, looks like this. That happens when your derivative is negative. So what I'm going to do is I'm going to take the second derivative, find my x values when my second derivative is equal to 0, and make a sign chart. So those of you who are obsessed with my YouTube, if you've seen my video on inflection points and increasing and decreasing functions, this is extremely similar, but we take it an extra step by taking the second derivative instead of the first derivative. All right, so first derivative, first things first, is going to have me bring down that 4, make it x cubed, bring down that 3, make it x squared, bring down that 2, multiply it to -3, giving me -6, x to the first, and you become 0. So that's first derivative. Second derivative is going to turn that 4 into a 12, 12x squared, turn that into a 6, so we got 6x minus 6. Now set that equal to 0 and factor. I'm going to factor out a 6, which gives me 2x squared plus 1 minus 1. I should be able to factor that out. So, I mean, one of them's got to be positive and negative. One of them's got to be 1. One of them's got to be x, and one of them has to have a 2 in front of it. So if it's going to be negative, I'd imagine this is the 2, because you have 2x times -1. Well, 2x squared, then 2x times -1, which is negative 2x. So I had it backwards. Let's move the 2 over here. Look at that. So x squared, 2x squared, minus x plus 2x minus 1. So that's what I need. All right, zero product property says that when you have factors multiplying to be equal to 0, you set each one equal to 0. Nothing happens here. If I have x plus 1 equals 0, then one of my inflection points is going to be -1 if I subtract 1 from both sides. If I take 2x minus 1, set that equal to 0, since I'm running out of space, add 1, divide by 2, my other inflection is going to be a half. Inflection point is going to be a half. So my inflection points, all 2 of them, are -1 and 1/2. I'm going to take that information and I'm going to make myself a sign chart. All right, I'm going to use the fact that I have -1 and a half, and I'm going to find the intervals. So what's going on between -infinity to -1? What's going on between -1 and a half? What's going on between a half and regular infinity? And I'm going to pick numbers in these 3 intervals, plug it into my second derivative, and see if I get a positive for concave up or a negative for concave down. So let's just pick the easiest numbers we can. I'll pick -10 for this guy. Let me move that down here. Will it make me do it now one by one? So let's do -10. Let's do 0. And let's do 1. So y double prime of -10 is going to be 12 times -10 squared plus 6 times negative 10 minus 6. Okay, let's do a little bit of mental math. Negative 10 squared is 100. 100 times 12 is 1200. 1200 minus 60 is still really big. Minus 6 is still really big, so we get a positive number here. So this is positive, meaning from negative infinity to negative 1, concave up. Okay, let's plug in 0 into our second derivative. 12 times 0 squared, I think I can handle that. Plus 6 times 0, I think I can handle that. Minus 6 is going to be 0 plus 0 minus 6, negative. So you're concave down. And let's see what happens when we plug in 1 to our second derivative. 12 times 1 squared plus 6 times 1 minus 6. 1 squared is 1. 12 times it is 12. 12 plus 6 minus 6 is still 12. Positive, positive. Now what this means is inflection points tell me where it's neither concave up nor concave down. That's the switch between concave up and concave down. Okay, that's what inflection points give me. This is the change. So what I know from this information is my graph is concave up on the intervals connecting negative infinity and negative 1, but not including negative 1 because it's 0 there. It's neither. And from a half to positive infinity. It's concave down in the interval where my second derivative was negative, and that happened between negative 1 and a half. So, like I said, very, very, very similar to critical points and increasing and decreasing. You just had to take this one step further. So in the end, a lot of work. Really not that bad, though. I like it. Find the relative extrema of y equals x cubed minus 6x squared plus 9x plus 1. Well, what's relative extrema, you ask? I got you. That's a cubic. This is a cubic. This is going to look something like that, give or take. Who knows exactly what it's going to look like. But extrema stands for maximum or minimum, or both, depending on what you're dealing with, or multiple. The reality of having a cubic function that looks something like this is this guy's going to continue going up and to the right forever and ever and ever. This guy's going to continue going down and to the left forever and ever and ever. And if someone's like, what's the maximum? Well, it's going to be infinity and infinity. What's the minimum? Infinity and infinity in the negative territory. Relative extrema says, all right, well, let's pretend that that's not going on. Tell me where this thing peaks out and bottoms out, ignoring the fact that we have forever going on the left and the right. Where it peaks out is called the relative maximum. So I'll just say rel max. Where it bottoms out is the relative minimum. Now, the way we're going to use calculus to figure this out is we're going to find where our equation is increasing and decreasing. When we find out that our equation is increasing and then decreasing, we have ourselves a relative maximum. When we find out where our equation is decreasing and then increasing, we have ourselves a relative minimum. So in order to find increasing, decreasing intervals, we need to first go with critical points, which requires the derivative. So let's start out with that. The derivative of y prime, is going to be drop that 3 down, make the cube to squared, minus 6x, drop down the minus, 2 times 6 is 12, x squared becomes x, and then 9x becomes 9. Excuse me. All right, so critical points. Set that guy equal to 0. Okay, so I'll put CP, not for Chris Paul, but for critical points. If you're watching this video and you're learning calculus, you probably don't even know who Chris Paul is. I want to factor this guy out. Let's bring out a 3. X squared minus, let's see, divide a 3 from that gives me 4. Divide a 3 from that gives me 3. Let's keep factoring. 0 equals 3 times, let me think, 2 numbers that add up to -4 and multiply out to +3 are going to be -3 and -1 in no particular order. Now, if 0 equals a bunch of factors multiplied together, I can use the zero product property and set each factor equal to 0. So 3 equals 0 means nothing. X minus 3 equals 0 means that I will have plus 3, you get 3. If I have x minus 1 equals 0 plus 1, you get 1. So my critical points are going to be where x is 3 and where x is 1. This is where my line should change from increasing to decreasing, decreasing to increasing, so on and so forth. So I'm going to make myself a little sine table, sine graph, whatever you want to call it, SIGN. I care about 1, I care about 3. Okay, and this is going to be my y prime sine graph. Now what I'm going to do is this is going to tell me which intervals is increasing or decreasing. I'm going to pick numbers inside each interval. So -infinity to 1, I can pick 0. 1 to 3, I can pick 2. 3 to infinity, I can pick, 10. And if I take these numbers, plug them into the derivative, and get a positive, it's increasing. If I get a negative, it's decreasing. So let's plug in 0. Y prime of 0 is going to equal 3 times 0 squared, which is 0, minus 12 times 0, which is 0, plus 9, which is a positive number. So this guy is increasing. Okay, this cubic is increasing from -infinity to +1, then hits a horizontal tangent and maybe does something different. We'll see. Let's plug in 2. Y prime of 2 is going to be 3 times 2 squared, which is 12, minus 12 times 2, which is 24, plus 9, negative. So this is decreasing. If I plug in 10, and again, I don't know why. I chose 10 because it's large enough where I should obviously tell if it's positive or negative. 3 times 10 squared is 3 times 100, so 300, like that movie. I forget what it's called. Minus 12 times 10, which is 120, so minus 120, plus 9 is definitely going to be positive. So when x equals 1, it goes up and then down. So at x equals 1, I have a relative maximum. At x equals 3, it goes down and then up, which means my graph is bottoming out. This is a relative minimum. Now, let's find the exact points. Okay, the way I find the exact points is I take those critical points that gave me a relative maximum or a minimum and I plug them into the original equation. So I'm going to plug in 1 to the original equation. So y of 1 is going to equal 1 cubed, which is 1, minus 6 times 1 squared, which is minus 6, plus 9 times 1, which is 9, plus 1. So 1 minus -5. -5 plus 9 is 4. 4 plus 1 is 5. So when I plugged in 1 to the original equation, I got 5. I'll deal with that in a minute. Well, no, I'll deal with it now. That tells me that my relative maximum, just one of them, is going to be the point 1, 5. Let's find out what my relative minimum is. All right, we'll plug in 3. So I have y of 3 is going to equal 3 times 3 times 3, 27, minus 6 times 9, so minus 54, plus 9 times 3, which is 27, plus 1. All right, so it's 27 plus 27 is 54, minus 54 is nothing, plus 1 is 1. So that equals 1. So my relative minimum is going to be 3, 1. Look at that. Didn't have to erase a thing. Aerosmith said, I don't want to change a thing. I said, I don't want to miss a thing. It's, I don't want to miss a thing. All right. This giant boot is my answer. Have fun with that. Find the absolute extrema on the interval -2, 4. Now I'm just going to make a random picture. Okay. In a previous video, we talked about relative maximum or minimum. And relative extrema is like, there's a relative max and there's a relative min, and there's a relative max and there's a relative mean. Well, absolute means, what if I take all of this and just like, we care about between here and here. So which one of these is the absolute maximum? Which one of these is the absolute minimum? You know, the absolute maximum could be right on the interval, or maybe it's not. Maybe the minimum is, I don't know. But now we're adding extra elements to it. So in order to do the absolute extrema, we still have to do the same thing that we would do for relative extrema, and that's find the critical points. First things first, I need the derivative. So y prime is going to equal 4, drop that down, x to the third minus 2x. Okay, drop the 4, make that a 3, drop the 2, make that a 1. So let me factor some stuff out. Set it equal to 0 and factor stuff out. I can bring out a 2x. When I do that, that becomes 2x squared. That becomes minus 1. When you have factors multiply together equaling 0, you're going to use the zero product property. Set each factor equal to 0. So 2x equal to 0. Divide by 2, x is equal to 0. 2x squared minus 1 equals 0. Add 1. Divide by 2. Take this square root and don't forget about your positive or negative. So my 3 critical points are x equals 0, positive square root of a half, and negative square root of a half. All right, so let's make ourselves a sign table with that one. We've got, let me see, this is y prime. We've got 0. We've got negative square root of a half. We've got positive square root of a half. So I guess the numbers that I can choose to go in between, I don't even know what square root of a half is. Let's consult the internet. What's the square root of a half? Okay, the internet says that this is negative 0.7 something. So while I plug in negative 0.5, why don't I plug in regular 0.5? Why don't I plug in negative 1? And why don't I plug in 1? Now, I'm going to plug it in to the derivative, because by plugging it into the derivative gives me the opportunity of finding increase, decrease, all of that good stuff. Whenever it goes from increase to decrease, it's a maximum. Whenever it goes from decrease to increase, it's a minimum. Okay, so I'm going to plug in negative 1 into the derivative. So that's going to be y prime of negative 1 is going to be 4 times negative 1 cubed, which is negative 4, minus 2 times negative 1. So negative 4 minus 2 times negative 1 is plus 2. So that gives me a negative, so you're decreasing. Okay, if I plug in negative 0.5, y prime of negative 0.5, I'm going to ask Siri to do this one for me because I don't have enough space to do it in my head. 4 times negative 0.5 cubed minus 2 times negative 0.5. All right, it's just positive. So you become positive. 4 times 0.5 cubed minus 2 times 0.5. That's negative. And let's plug in 1. I can do that without my old friend Siri helping me out. That's going to be 4 times 1, 1, which is 4, minus 2 times 1, which is 2, which is positive. So there you have it. All right. So I have a relative minimum. I have a relative maximum. I have a relative minimum again. So this picture is going to look something like this. Okay. It's going to look something like that. Here's the problem, though. What if, like, that is 4? Wouldn't that mean technically, since that part right there is higher than everything else, wouldn't that mean that the intervals 2 could be an option for an extrema? Yeah. So what I'm going to do is I'm going to take my 3 critical points and I'm going to take my 2 intervals and I'm going to plug them into the original equation to see what values I get. The largest value that I get is going to be my absolute maximum, and the smallest value that I get is going to be my absolute minimum. So let's start out with the endpoints. Let's just do it. Okay, y of negative 2 is going to be the same as negative 2 to the positive 4th power, which is 2 times 2 is 16, minus negative 2 times negative 2, which is 4. That gives me 4. No, it gives me 12. It gives me 12. Trying to do too much. All right, so one endpoint, check. The other endpoint, about to check. 4 to the 4th is going to be, I believe that's 256. 4 to the 4th power. 256. 256 minus 4 squared, a fun game, becomes 240. Definitely going to need Siri for these ones. Y of negative square root of a half. Oh, I already know what that one's going to be. Jumping the gun. Jumping the gun. Or do I? Do I? No, I don't. If I do 1 times 1 times 1 times 1, right, I get the square root of 1 on top, which is 1. If I do 2 times 2 times 2 times 2, that's 16. So the square root of 16, I get a 4th on the bottom, minus the square root, negative square root of a half is just a half. So you become negative 3/4? Yeah. No, negative 1/4. A little paranoid about that. What is the square? What is the square root? Oh my goodness gracious! What is the square root of 1/2 to the 4th power? Yeah, all right. I did it right. I did it okay. What's a quarter minus a half? Negative 0.5. All right. Let's plug in 0. Finally, an easy one. You're going to get 0. And if I plug in positive 1/2 in a square root, it's going to give the same thing as that. So this is fun. I have an absolute maximum for sure, and it's u. So my absolute maximum is the point 4, 240, and I have 2 absolute minimums. And my absolute minimum is going to be the points negative square root of 1/2, negative 1/4, and positive square root of 1/2, negative 1/4. Whew, gross. Didn't like it. But it's done, and it's done, and it's done correct and well. A supermarket employee wants to construct an open-top box from a 14 by 30-inch piece of cardboard. So that was me trying to draw a rectangle. Let's try it one more time. There we are. Not bad. So we'll call you 30. We'll call you 14. That is sentence number 1. Sentence number 2. To do this, the employee plans to cut out squares of equal sides from the 4 corners of the 4 sides and bend it upwards. All right, so we're starting to get a picture here. Here's a square. We'll call you x. Here's a square. We'll call you x. Here's a square. We'll call you x. Here's a square, we'll call u x. So each sides here of the square are called x's. Lots of x's, kind of like me and my dating history. Hey-o! It's not true. What size should the squares be in order to create a box with the largest possible volume? So let's try to visualize what's going on here. All right, after we cut out these x's, let me try to draw a picture that looks like that. Not bad. Can I make it smaller? Yeah. All right. That's the best I can do. Let's move that over. Let's do that. Oh, not bad. Let's do that. Let's do that. Not bad again. And let's do that. And let's do that. I'll take it. So what's going to happen is we're going to take that and we're going to bend these upward. Bend them up, bend them up, bend them up. When you bend them up, you have yourselves a cardboard box without a top to it. Okay, cardboard box without a top to it. That's me attempting to draw a cardboard box. It looks awful. But there you have it. Now, I have to figure out what these measure up to. Well, if I were to fold that up and pretend that this is that, this side length is not 14. It's 14 minus x because I cut out 2 of the sides there. Again, when I bend that up, this is that. This little length is that. And so that length is 14 minus x, so 14 minus 2x. Similarly, this whole thing was 30. But after I bend these up to create that length, it's 30 minus 2x. And then I have the height. Since I bend it up, it's going to be the size of the squares that I cut out, x. My job is to maximize the volume. So we need to write ourselves a volume formula. So volume is normally length times width times height. In this case, our volume is going to be that times that times that. So we have x times 30 minus 2x times 14 minus 2x. So it doesn't really matter. We're going to have to multiply things anyway. So let me distribute that x. I have x squared in parentheses, just kidding, 30x minus 2x squared. I don't know why I jumped out to x squared. But we have 30x, x times negative 2x is negative 2x squared. And then we're going to FOIL that out to 14 minus 2x. All right, so 30 times 14. That's 420, so we've got ourselves 420x. 30x times negative 2x is minus 60x squared. Negative 2x squared times 14 is going to be minus 28x squared. And then 2x squared, negative 2x squared, and negative 2, positive 4x to the third. Let's combine like terms, put this all in standard form. We've got ourselves 4x cubed, negative 88x squared, and positive 420x. Now, I found my volume formula, and there it is. If I'm going to maximize it, I need to take the derivative and find critical points. This is very, very, very similar to when you do extrema, maxes and mins. But I'm going to add a little extra thing to it. It's not just relative extrema. I have to go one step further. Before I even do any of that, I got to get critical points. So v prime is going to equal 12x squared. Let's multiply that minus 176x plus 420. Get rid of the x and stop making so many typos and writing errors. Now, in order to do critical points, I have to set it equal to 0, and I'm going to factor the 12 out because I think I can. Oh, I can't factor out a 12. Well, this is frustrating. Let me see. I can factor out a... Can I factor out a 6? No, I can't, but I can factor out a 4. If I do that, that leaves me with 3x squared minus, what is that, 44x plus 105. All right, I could use whatchamacallit if I wanted to. Quadratic formula, but give me one second. Oh, you know what? That's 35 and 3. 35 and 3. Ooh, 3x minus 35 and x minus 3. All right. I'm going somewhere. So my critical points so far are going to be, if I set these each equal to 0, okay, first off, 4 means nothing. If I set that equal to 0, one of my critical points is 3. If I add 35 and divide by 3, that gets me 10 and 2/3, I believe. No, 11 and 2/3. But since this is a maximization problem, I'm bound by real life endpoints. So this is more like the absolute maximum and minimum where I have an interval to deal with. If I'm cutting x's out, I can't cut any more than 7. So I have legitimate endpoints of 0 because I can't, have 0 squares to cut out. And I can't go further than 7. If I were to try to cut out x's, if I were to try to make 8 my x, that's too much to cut out. So 7 is one of my endpoints and 0 is one of my endpoints. But since I found out that 7 is an endpoint, you can't work. So what I'm going to do is I'm going to find the volume using this formula right here by plugging in 0, which I know will not work, 7, which I know will not work, and 3, which is going to have to work. So let's do it anyway. Volume of 0 is going to be blah, 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 0 cubed minus blah, blah, blah times 0 times plus blah, 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 0. So I get 0. So that makes sense. If I can't fold it up, I get 0. Now let's try 7. If I plug in 7, the original volume problem gave me that. So 14 minus 2x. So what's going to happen is this part is going to become 14 minus 14. So let's just make believe that you understand what I'm doing. If I were to plug in 7, I'm going to get 0 again. So 3's got to be my only guy. So let's plug in 3. 4 times 3 cubed minus 88 times 3 squared plus 420 times 3. It's going to give me some number. And what it's asking me here is you don't have to find that number. Just find out the sizes of the squares in order to make it work. Well, 3 is going to be my guy. So 3 inches is going to be my answer. So maximization problems, optimization problems are pretty brutal, this being one of them. But, you know, after all of that work, I think we finally figured that out. It's not going to be the prettiest answer, but it'll do. Okay, let's sketch a graph using rules for increase, decrease, and concavity. So we're not looking for perfection, we're looking for somewhat accuracy. Let's do the first thing by doing increase. In order to find increase and decrease, you're going to take the derivative, which gives you critical points. So let me write that over here. It's going to be fun trying to fit this all in one screen. Probably not going to happen, but that's all right. Critical points are going to be found by taking the derivative. So you're going to bring that 4 down, and the 4 over here cancels each other out. So that leaves you with negative x cubed plus 2x, and then nothing. Set it equal to 0. Let's factor out a negative x. Yeah, let's factor out a negative x. When we factor out a negative x, that leaves us with x squared minus 2. Set these both equal to 0. So 0 is going to equal x and negative x, which means x equals 0. Sorry if I jumped ahead too fast. X squared minus 2 equals 0. Add 2 gives you this. Square root both sides. Don't forget to attach a plus or a negative over here. And so my critical points are going to be negative square root of 2, 0, and the square root of 2. So remember when I said about a minute ago, it's going to be hard putting all this on one screen? It ain't happening. But what I have right now is I have a critical points concavity, or not, sorry, not concavity, critical points increase, decreasing starting point. So I'm going to make myself a sign chart, S-I-G-N, not S-I-N. We're going to put negative square root of 2 on there. We're going to put 0 on there. We're going to put positive square root of 2 on there. In order to find increase and decrease and where that happens, all right, I'm going to pick numbers that aren't exactly these guys but live on the interval. So I can pick like, I don't know, negative 5, negative 1, 1, and 5. I'm going to plug these into the derivative, which is this guy right here, do a little bit of math. If I get positive, that means it's increasing on that interval. If I get negative, that means it's decreasing on that interval. So let's take our y prime and plug it in. Y prime of negative 5. Let's try to do this mentally. All right, negative 5, there's my derivative. Negative 5 is going to be, negative 5 cubed is going to be negative 125. That negative cancels it out. So 125 minus 10 is going to be positive. So this is increasing here. If I take y prime of negative 1 and plug in negative 1, I get negative 1 to the third power, which is negative 1, times the negative 1, which is positive 1. But I'm going to add positive 1 to 2 times negative 1, which is negative 1. So this is negative. Again, if you're like, what happened? Just throw it in a calculator, buddy. Trust me on this one. Y prime of 1. Okay. Negative 1 cubed is negative 1 plus positive 2 is going to be positive. So I'll move that over there. Positive. And then if I plug in regular 5 into the derivative to see if it's positive or negative, I will get 5 cubed, which is 125. That negative out there is negative 125. Negative 125 plus 10 is still pretty negative, which means that's pretty decreasing. So this is what I know so far. This guy is increasing all the way up until negative square root of 2, whatever square root of 2 is, like 1 point something, 1.7, I believe. Maybe not, maybe 1.4. I'll ask Siri to help me out with that one. And then it starts decreasing. It hits an x of 0, so it hits the y-axis, starts increasing again, and at square root of 2, it starts decreasing again. So this is happening like that. But that's not good enough. Need more specifics than that. Need a lot more specifics than that. So what I'm going to do is I'm going to start my inflection points up here. I'll probably end up erasing that when all is said and done, but we'll see. We'll see what I can fit on this one little screen. So to find the inflection points, I care about the second derivative. So the first derivative was negative x cubed plus 2x. So the second derivative has me bringing that 3 down and squaring it, negative 3x squared, and then getting rid of that x to make it plus 2, and I really hate this problem. Inflection points, set it equal to 0. Let's factor out a negative 3. No, let's not factor out a negative 3. Let's just leave it like that. Factoring out a negative 3 gets me nowhere. I could subtract 2. Negative 2 is equal to negative 3 over x squared. Divide everything by negative 3. Divide everything by negative 3. I get 2/3 equals x squared. Square root both sides, positive or negative, and my inflection points exist at the square root of, I forgot to write out square root. My inflection points exist at negative square root of 2/3 and positive square root of 2/3, like that. So I'm going to make another sign table. But this time, this is going to be for concavity. So let me put my concavity info right here. All right, I have negative square root of 2/3 and positive square root of 2/3. Now, the square root of 2/3 is, I know, somewhere in between 0 and 1. So again, I need to choose numbers that live in between these intervals, but not exactly on those intervals. So I'll choose 0, I'll choose negative 1, and I'll choose positive 1. So when I find the y double prime of that number, it'll tell me if it's positive or negative. If it's positive, it's concave up. If it's negative, it's concave down. So y prime of negative 1, if I plug in negative 1 to y double prime, I'm going to get negative 3 times negative 1 squared. So negative 3 times 1, negative 3 plus 2 is negative. So right here we have concave down. If I plug in 0 for y double prime, I get 0 plus 2, which is positive, concave up. And if I plug in regular 1 to y double prime, so y double prime of regular 1, I get literally the exact same as I get over here. So I get negative, which makes that concave down. All right, time to sketch. Now, again, the purpose of sketching is you're not looking for perfection. You're looking for like an accurate representation of what this picture looks like. So what's the lightest color that I can use on this thing? Like a nice yellow. Let's get a nice yellow up in here, like a gold. All right. So there's my coordinate plane that is awfully drawn. You can barely see it. The critical points and the inflection points are what really matter. Okay, so I care about the square root of negative 2. I care about the square root of 2/3, the negative square root of 2/3. I care about 0. I care about the positive square root of 2/3. And I care about positive square root of 2. And I think I've hit everything. Negative root 2, negative, I got it, 0's there, I got it. Now let's do some drawing. I increase, I'm increasing until I hit negative square root of negative 2. So let's draw something that's increasing. Once I hit negative 2, I begin decreasing. until I hit 2/3. Once I hit 2/3, I start going concave up. So right now, you can see that negative 2/3 to the left is concave down. But once I hit negative 2/3, I start concave upping until I hit 0. Once I hit 0, my decrease becomes an increase and continues that trend until I hit negative square root of 2/3, where I become concave down again. Once I hit the square root of 2, my increase becomes a decrease, and so I get some kind of weird thing that looks like that. All right? Again, this is a sketch. This is not perfection. If I wanted perfection, then I would take all of these numbers, plug them into the original function, and get specific points. I could have done that, but I didn't. You know why? Because I have one screen here and I don't have all the time in the world. And I'm sure I have a video somewhere on the internet that involves me doing this. So, go find it and like and subscribe while you're at it. All right? That's that. Bye. A particle moves along a horizontal line where its position is given by the function below. S of t equals t cubed minus t squared minus 5t. Find the velocity and acceleration at t equals 3 seconds. Well, let's do this. Let's do the velocity on the left. Let's do the acceleration on the right. All right, let's do the velocity function in red, or if you're colorblind, gray. Velocity is found by taking the derivative of your position function. Okay, so this. So I need to take the derivative of s. So s prime is going to be drop down that 3t squared minus 2t minus 56. Okay, power rule, power rule, power rule. This is the velocity function right there. Let me rewrite it out. The velocity function is 3t squared minus 2t minus 56. What I care about is what happens at 3 seconds. So v of 3, which is s prime of 3, is going to be 3 times 3 squared minus 2 times 3 minus 56. Okay, 3 times 3 times 3 is 27, minus 6 minus 56. The negatives combine to make negative 62. Negative 62 plus 27 is negative 35. So that's the velocity at 3. Okay, what this means is I have seconds here, units. It doesn't say feet. It doesn't say any, measurement. What this means is this is going backwards, okay, or downwards. If it's a negative velocity, that means you're like, if I were to drive 35 miles an hour, I'm driving forward. If I were to drive negative 35 miles an hour, I'm driving backwards 35 miles an hour, and this represents going backwards. Now, if the velocity, which is speed, right, but velocity is allowed to be negative, speed's not. So just another thing to put in another feather to put in your hat. If I wanted to find acceleration, acceleration is the second derivative of the initial function, of the position function. So s double prime of t. So this is going to be my acceleration function. So s single prime, its derivative, drop that 2 down, becomes 6t minus 2, get rid of the t. This is the acceleration function. Let me get rid of the prime. Oh my gosh, I really didn't need that prime there, and so I just got rid of everything. All right. The acceleration function is given to us by 6t minus 2. Now, acceleration is what's going on at the moment. So what's happening at 3? Are you accelerating? Are you decelerating? Are you speeding up? Are you slowing down? Let's find out. A of 3 is going to be 6 times 3 minus 2, which is 18 minus 2. So A of 3 is 16. So let's attach units of measure to this, right? Velocity is like miles per hour, feet per second. I have 3. It doesn't give me a unit for its position, so we'll say units per second. For acceleration, it's units per second squared. Now, what's happening at this 3-second mark is I'm hitting the pedal to the metal. I'm accelerating. I'm going faster, but I'm going backwards while doing it. So in a second, I'll be going negative 38 miles an hour or something like that. But acceleration is positive, which means I'm speeding up while going backwards. That is how we do this problem, and that is the velocity and acceleration example dunzo. All right, let's calculate the limit of this guy right here. We have the limit as x approaches 0 of e to the x minus e to the x, negative x, all over x. So I guess if I plug in 0, I get 1. If I plug in 0 again, minus 1, I get 0 on the top. But if I plug in, oh no, 0 over 0, that's not possible. That's indeterminate. Well, there is a section from early on in calculus that says this is no good. You can't have 0 over 0. Can't have it. So what happens when you do that? Normally you try to find ways to make this just one, like this one function or this one fraction, not one fraction, but I can't do that here. So there's a rule called L'Hopital's rule that says that this guy is equal to the derivative of the top over the derivative over the bottom and take the same limit. So what I'm going to do is I'm going to take this guy, I'm going to rewrite the limit as x approaches 0 of e to the x. So I'm going to take the derivative of e to the x. So e to the x is e to the x minus, I'm going to take the derivative of e to the negative x. So this is chain rule. The chain rule says you take the derivative of the outside, which is e, so e, keep the inside, but multiply everything times the derivative of the inside. So the inside is negative x, the derivative of negative x is negative 1, so just make that negative. So e to the negative x became negative e to the x, so this becomes e to the negative x, positive. Take the derivative of the bottom 2, that becomes 1. Now I plug it in and see what happens again. So I get e to the 0 plus e to the negative 0 over 1. E to the 0 is 1. E to the negative 0 is the same thing as e to the 0, which is 1 over 1, and I get 2. So again, the trick here is if you plug in your limit and you get 0 over 0, which is impossible, take the derivative of the top, take the derivative of the bottom, try it again. If it happens again, do the exact same thing. Repeat until you finally get yourselves a solid number, which is what I got. The answer here is 2. Let's calculate the limit of x going to x or pi over 2 of 3 secant x minus 3 tan x. So let's just plug this stuff in. X goes to pi over 2, 3 secant, wait a minute. Secant pi over 2 is undefined. I can't do this. This is going to be an undefined answer. So what do I do if it's an undefined answer? Do L'Hopital's rule. L'Hopital's rule says that, let's do this. Let's make life a little easier. Let's rewrite these guys out. L'Hopital rule says that if we get something that's undefined, we could take the derivative of the fraction, the derivative of the top over the derivative of the bottom. Well, I don't see a fraction there, but you know what I do see? Let's write this out and let's get rid of all this limit stuff. I'll attach it later. Okay, 3 secant x. Secant is 1 over cosine. So this is the same thing as 3 times 1 over cosine x. Tangent is the same as sine over cosine. So sine x over cosine x. Now let's write this out a little more convenient. Let's put the 3 up top. Let's put the cosine on the bottom. Now, why did I make that one big denominator? Because these two will combine. So on the top, minus 3 sine x, so minus 3 sine x. And now what I can do is take the derivative of this guy, of the top, and the derivative of the bottom, and see what magical things happen. Now, by the way, if you're wondering, well, why can't I just plug in pi over 2 into x? Because cos of pi over 2 is 0, so you're still going to get undefined. So x is pi over 2. Let's take the derivative of the numerator. The derivative of 3 becomes nothing. Now I have negative 3 sine x. The derivative of sine is regular cosine, so I'm left with that. In the denominator, let's take the derivative of cosine, which is negative sine x. So now what I have is, and I'm writing this out knowing that there's a possibility that I might have to keep going, but we'll see. We'll see. Negative over negative is a positive. I now have 3, and cosine over sine is cotangent. So I have cotangent x. Now what I'm going to do is I'm going to calculate 3 times the cotangent of pi over 2. Now the cotangent of pi over 2 is 0. And 3 times 0 is 0. So at the end of the day, this whole thing has a limit of 0. Now we know that with limits, you're not looking at exact answers, because if I were to try to, once again, plug in pi over 2, it's not going to work. It's going to be undefined. But where is my graph going as I approach pi over 2? To 0. It works out. You get a hole there, but that's all right. That's my answer. L'Hopital's rule. Evaluate the indefinite integral. Here it is, the indefinite integral right there, negative 24x to the 5th dx. Now what the indefinite integral does is it does the reverse of a derivative. So with the derivative, we would see something like this and think power rule. Well, the integral has its own version of a power rule, and it looks like this. I'm going to let a be a coefficient, x is x to the n, and dx is basically just telling you, the end. When you take the integral, the indefinite specifically integral, because there is a definite integral, you'll see videos on that later on, what you do is the a is just kind of there. You multiply everything to 1 over n plus 1, and then you add 1 to the n. Guess I should do that. And you add this arbitrary c. Now, what's that c stand for? A constant. You have to put plus c on an indefinite integral because that c could represent any constant that we just don't know. So the way I apply that here is if I want to take the integral of negative 24x to the 5th, my a would be negative 24. I'm going to multiply that to 1 over, there's my n, 5 plus 1, x to the 5 plus 1. Close it, add c. Negative 24 times 1 over 6, x to the 6 plus c. And that negative 24 times positive 6 becomes negative 4, x to the terrible looking 6 plus c. That's my answer. As time goes on, you could do some mental math and realize that when you do stuff like, add 1 to 5 and bring it down, that will become automatically negative 4 as time goes on, but let's not jump the gun. Okay, that's the power rule for the indefinite integral. Evaluate the indefinite integral. Now, if we are given an indefinite integral of a polynomial that requires power rule for one of them and power rule for the other, you're just going to take the integral of each. Okay, there's basically a rule that says if I'm going to do this, then I'm just going to do this. Negative 9x squared dx plus the integral of 10x dx. Now, as time goes on, you don't need to write out all of this. You can just realize that you're doing the integral for each one on its own, but why not have some fun? If I were to use the power rule, what I do is I bring out a negative 9. I write out 1 over the exponent plus 1, x to the exponent plus 1, right? Normally I would put a plus c here, but I'm going to save that for the very end because I have another indefinite integral that I have. So I have a 10. I have an invisible 1 for my exponent, so why don't I just put that there? So 1 over your exponent plus 1, x to your exponent plus 1. Now I'll drop that plus c. So this leaves me with negative 9 times 1 over 2 plus 1, which is a third, x to the third, plus 10 times 1 over 1 plus 1, which is a half, x to the second, plus c. Do a little bit of simplifying. Negative 9 times a third is negative 3. Negative 3x cubed plus 10 times a half is 5. 5x squared plus c. And we can see if we wanted to do a quick derivative of this, multiply 3 times negative 3, we do get negative 9x squared. Multiply 2 times 5, we do get 10x. And take the derivative of any random constant, you do get 0. We did it right. That's my answer. That's the indefinite integral of a polynomial. Evaluate the indefinite integral of negative 5 cubed root of x squared over 3. So let's do a little bit of rewriting. Okay, let's write this out as negative 5 thirds. And let's turn this into x to the 2 thirds dx. Where did I get that 2 thirds from? A cubed root becomes an exponent of a third. A square becomes an exponent of 2 still, so 2 thirds. Now what I'm going to do is I'm going to use the power rule on this guy. It's not going to be pretty. Not going to be pretty. Let's bring out the negative 5 thirds. I have 1 over. Now I'm going to add 1 plus 2 thirds x to the 2 thirds, plus 1, plus c. Okay. Negative 5 thirds, still. 1 plus 2 thirds is the same as 3 thirds plus 2 thirds, so we can write this out as 1 over 5 thirds x, 2 thirds plus 1, again, same exact thing, 5 thirds, plus c. 1 divided by a fraction becomes its reciprocal. So this becomes negative 5 thirds times 1 over 5 thirds is 3/5. How convenient. X to the 5 thirds. Why is that convenient? Well, 5 thirds times 3/5 cancel each other out. So we get negative x to the 5 thirds plus c. And many teachers, professors might be okay with this, but if they want you to change it, you can write this out as negative cube root of x to the 5th plus c. Either one of these are acceptable, but there they are in both of its forms. Fun. Evaluate the indefinite integral. So I have 3x to the negative 1. Now let's be careful. I can rewrite this out as this. And normally I wouldn't like, normally I like having an exponent there. Normally I'm turning this into this, but the reason why I'm writing this out is because of a rule that says that the integral of 1 over x is ln of x. with the absolute value. So if I wanted to be super, super, super picky math teacher, what I could do is I can bring out that 3, because you're allowed to do that with integration, and that leaves me with 3 times the integral of 1 over x dx, which means, according to this rule over here, I get 3 times 1 over x So that means I get 3 times ln of the absolute value of x plus c. That 3 times ln of x just gives me 3 ln of x. And if you're like, should I distribute the 3 to the c? No, because we don't even know what c is. Just leave it like that. Technically, it's not wrong if you wrote out 3c, because again, it's just some arbitrary constant. But we don't have to. And so that's our answer. We just did the indefinite integral of x to the negative 1, also written as 1 over x. So the integral of x to the negative 1 is ln of x. Just be careful, because it's tempting to do the power rule. No power rule here. Evaluate the indefinite integral of negative 5 sine x. Now, you might remember from back in the day that the derivative of cosine x is negative sine x. So it would make sense to us to say that the derivative of sine x, positive sine x, is going to give me negative cos x. Let's put the dx there to make it complete. Let's put the plus c there to make it complete. Now, why is all this important? Well, if I wanted to write this out as a picky math teacher, I could rip out that negative 5 and say the integral of sine x dx. That's a d. I need my x first. So there you have it. So I can now use this rule, negative 5 times the integral of sine x is negative cos x. There you go. Plus c lives right there. Negative 5 times negative cos is positive 5 cos x plus c. So that, ladies and gentlemen, is the integral of a sine function. Bada bing. Evaluate the indefinite integral of negative 3 cosecant x times cotangent x dx. You may have learned that back in the day, the derivative of regular cosecant x is negative cosecant x times cotangent x. You may have learned that. Well, look at the similarities. What this means is the integral of cosecant x cotangent x is going to be negative cosecant x. Now, I know that this is a negative, and if I wanted to apply the negative and do a little bit of reverse, that's fine, but I'm not going to. What I'm going to do is I'm going to rip out that negative 3 because I can. I have the integral of cosecant x times cotangent x dx. I now know that the integral of cosecant x cotangent x is negative cosecant x, and then we're going to attach that plus c. So negative negative becomes positive. 3 cosecant x plus 3. That's my derivative. Nope, just kidding. That's my integral. I need to take a break. Thanks for watching. Evaluate the indefinite integral 12x cubed times the quantity 3x to the 4th plus 4 all to the 4th power. Now, what I could do is I could FOIL this out and then FOIL it again and then FOIL it again and then distribute to 12x cubed, but that would be an absolute nightmare. So what I'm going to do is use U substitution. It's very similar to chain rule for derivatives where it looks like you have a function living within a function. But U substitution is basically saying I need to find, there's two parts here, the 12x cubed and the stuff inside the parentheses. You're basically saying, is there anything that if I were to take the derivative of it, I see floating around in the problem? Yeah. It looks like that if I were to take the derivative of something x to the fourth, I would get something x to the third. So what I'm going to do is I'm going to let u equal 3x to the fourth plus 4. Okay, I take the derivative of that. Du dx means the derivative of u with respect to x. 4 times 3 is 12. 4 drops down to a 3, and this 4 goes away. Now, what I need to do is I need to solve for dx. The way I solve for dx is I multiply both sides by dx, and as you do more of these, this process will go a whole lot faster. But if I multiply both sides by dx, I have du equals 12x to the third dx. Dx isn't all by itself yet. I'm going to divide both sides by 12x to the third. Divide both sides by 12x to the third. And now I have dx equals du over 12x to the third. Now, why does that matter? Because what I'm going to do is I'm going to replace what I called u with u, and I'm going to turn dx into du over 12x to the third. And you'll see the magic happen. So I have 12x to the third. That whole thing is now u to the fourth, and dx is now du over, no way, 12x to the third. Now, what's magical about that? Well, 12x to the third over 12x to the third cancels each other out. So now I have the integral of u to the fourth du. The integral of u to the fourth du is 1/5 u to the fifth plus c. Now, before I circle this and call it a day, I'm not done. Remember, we were not given u in the original problem. We were given something with x's in it. What I'm going to do is I'm going to rewrite this guy, turn u into 3x to the fourth plus 4. So my final answer is going to be 1/5 parentheses 3x to the 4 plus 4 close parentheses to the fifth power plus c. That is my guy. That is my answer. That is u substitution dealing with polynomials and power rule. Fun! Evaluate the indefinite integral. All right, so what I have here is I have a rational function. X is on top, x is on the bottom. And the way I'm going to approach this is with u substitution. What you do with u substitution is you look at what you have. So I have two things here, the numerator and the denominator, and see if I were to take the derivative of one, that I'd get the other, or see if that's floating around somewhere in the problem. If I were to take the derivative of the denominator, I would get that guy right there. So what I'm going to do is I'm going to let u equal the denominator, 4x to the fifth plus 3. Now what I want to do is I want to take the derivative of that, du dx equals, we'll drop that, make that 20x to the fourth plus 3 goes away. What I want to do is I want to turn this into dx. So the way I turn this into dx is I multiply both sides by dx. So du equals 20x to the fourth dx. Divide both sides by 20x to the fourth. Divide both sides by 20x to the fourth, and now writing it out a little bit nicer, dx equals du over 20x to the fourth. Let's go back to my original integral. I can replace a few things. I know that I didn't do anything with 20x to the fourth, so that happens. I called u 4x to the fifth plus 3, so let's call u, and I called dx du over 20x to the fourth. Now, why is this fantastic? because these guys cancel out. And that's what you're hoping will happen. If you're going to use u substitution, you need all of your x's to go away. Otherwise, you chose the wrong u. So now what I have is perfect 1 over u du. The integral of 1 over u is ln of u. Add that arbitrary c. I'm not done. I said that u was 4x to the fifth plus 5, so my final answer is going to be ln of 4x to the fifth plus 3 in absolute values plus c. So a little bit of rationals, a little bit of ln's, a little bit of u, a lot of bit of me, and a lot of bit of fun. Evaluate the indefinite integral. We have 10 sine of, let's put this in parentheses so it looks a little bit bigger, of negative 2x times e to the cos negative 2x. What you want to do is whenever you have weird looking integrals, like we have something times something to the something, we want to try to use what's called u substitution. And when you use u substitution, you want to pick a u that if you were to take the derivative of it, you see that derivative floating around somewhere else in the problem. Now, what I'm going to do is I'm going to let u equal cos of negative 2x. I almost said cos minus 2x. It's cos of negative 2x. Because if I take the derivative of cos, I will get something like sine, which is what I have there. Things will cancel out. U substitution, that's what you do. So what I have to do is I have to find the du dx. So du, the derivative of cosine of negative 2x involves chain rule. So you take the derivative of the outside stuff, which is negative, and I'm going to purposely leave a little space here, negative sine. Okay, the derivative of the outside stuff is negative sine stuff. Keep the inside stuff, but multiply everything by the derivative of the inside stuff. So the derivative of the inside stuff is going to be negative 2. So I have a double negative going on here, which I'm just going to say du dx is going to equal 2 sine negative 2x. Now what I'm going to do is I'm going to multiply both sides by dx. That gives me du equals 2 sine negative 2x dx. I'm going to divide everything by this. That way it gets dx all by itself. Divide everything by 2 sine stuff. And what I'll end up with is dx equals du over 2 sine negative 2x. So let's rewrite this guy out knowing what I know. I have the integral. We could bring that 10 out. Why not? The integral of sine of negative 2x times e to the u. And instead of dx, I'm going to write out du over 2 sine of negative 2x. The magical thing that happens here is the sine stuff disappears, which should happen. Anything that involves the x's should go away if you do this. Should have crossed all that out. All right, 2 is on the bottom, 10 is on the top. This becomes 5. So I have 5 times the integral of everything is gone except for e to the u du. Okay, the integral of e to the u is e to the u. So I have 5e to the u plus c. What was u? Well, my final answer is going to be e to the cos negative 2x. Don't forget about your constant floating around at the end. That is my answer for this indefinite integral. Fun, 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 fun. Evaluate the indefinite integral 16x squared times secant squared of 4x to the fourth minus 2. All right, so when we have a product of functions, which is what I have, and I'm being asked to integrate, I'm going to try to find a u. That if I were to take the derivative of it, its derivative is floating around somewhere else in the problem. If I were to take the derivative of something x to the fourth, I would get something x to the third. So I'm going to let u equal 4x to the fourth minus 2. This is called u substitution. I have like a billion videos of u substitution, like maybe 3 or 4 of them. All right. What you do next is you take du dx, which means the derivative. You get 4 times 4, which is 16. That 4 drops down to a 3, and that minus 2 goes away. Oh, look at that. The same exact thing over there. It's as if that's supposed to happen. Now I need to solve for dx. So you're going to multiply both sides by dx, giving you du equals 16x cubed dx. In order to get dx all by itself, divide everything by 16x squared. So you're going to have dx. I'm just flipping things around. I'm dividing and flipping. Du over 16x cubed. Now I'm going to rewrite this integral. Okay. 16x to the third times secant squared. That became u. And dx became du over 16x cubed. Good things happen because the 16x cubed and the 16x cubed goes away. If you're doing integration by substitution or u substitution, if you are trying to get u in here, all the x's have to disappear. If that doesn't happen, you did something wrong. You selected the wrong u. So now I have the integral of just regular old secant squared u du, no attachments. The integral of secant squared stuff is tangent stuff. So regular old tangent u plus c. Can't circle it because the original problem didn't have u in it. I called u 4x to the fourth minus 2, so I have to rewrite this out and say tan 4x to the 4 minus 2 plus that arbitrary constant. Another u substitution problem down. 10 u so much. Like and subscribe. Approximate the area under the curve. All right, so what I'm being asked to do is I'm given a function here on an interval of -5 to 3. I'm going to actually be as approximate as humanly possible, right? I have, let's see how many boxes that I have. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. These combine to make 33. These combine to make 34. These combine to make 35. And these combine to make 36. Now, the CUDA software answer is 36 because that's where I stole this problem from. In reality, what you could probably do is count the entire whole squares and then maybe do some half squares and get a more accurate answer. But, you know, what they want us to do is they want us to turn this problem into these rectangular things where it looks like the rectangle is hanging all the way to the left side of whatever double interval, I almost said integral, it gives us. And that's that. Evaluate a definite integral between -1 and 3 of this polynomial right here. Now, what we do is called the fundamental theorem of calculus. All right, you take the integral, you find whatever that is, okay, and capital F stands for integral, and then what you do is you take, this is called the upper limit, and subtract the same exact integral and plug in the lower limit. This is the fundamental theorem of calculus, the FTOC. All right, so the first thing I have to do, as I erase that, is I have to take the integral. No plus c's in this. We are finding absolute answers. All right, you're taking the integral of negative x to the third plus 3x squared plus 1. So a lot of power rule going on here. So we have negative 1 over, take that 3 plus 1, x to the 3 plus 1, plus 3 over x, which is 2 rather, plus 1, x to the 2 plus 1, plus, if it's just a constant, when you take the integral of a constant, attach an x. And then these little things over here are just reminding me that I have these limits of integration that I'm going to eventually plug in. So let's clean this up. Negative 1/4 x to the 4th plus 3 over 3 disappears, x cubed plus just an x with my limits being 3 and negative 1. Now, the fundamental theorem of calculus says is I'm going to take this whole thing, plug in 3, minus take this whole thing, plug in negative 1. So a little bit of math. Hopefully I saved myself enough room. I feel like I didn't, but I guess we'll find out. Negative 1/4. My upper limit is 3, so 3 to the 4th plus 3 to the 3rd plus 3, close it, minus negative 1/4. Negative 1 is my lower limit to the 4th plus negative 1 to the 3rd plus negative 1, close that. All right, let's see how much math we can do and not make any silly mistakes, which is bound to happen. Bounds, that's funny. Math humor. Math humor. All right, we've got negative 1/4 times 3 times 3 times 3 times 3 is 81. So negative 81/4, don't like that, plus 3 to the 3rd, which is 27, plus regular 3, which is regular 3, minus negative 1 to the 4th, which is regular 1 times negative 1/4, so negative 1/4, plus negative 1 to the 3rd, so minus 1, plus negative 1, so minus 1 again. All right, let's change colors. All right, so I'm just going to use decimals because that's probably the easiest way to go. That's negative 20.25, right? Negative 20.25. This guy becomes 30, so negative 20.25 taken away from 30 is 9.75, minus negative 1/4 minus 2, so negative 2 1/4. All right, double negative becomes a positive. 9.275 plus 2.25 is going to give me a nice 12. And that's the fundamental theorem of calculus for you. Can't spell fundamental theorem of calculus without fun. Oh, the answer is 12. All right. We have a definite integral of 2 cos x. Upper limit is negative pi over 6. Lower limit is negative pi over 4. This uses the fundamental theorem of calculus, which says take the integral, plug in this guy, minus sign, plug in that guy. So hopefully we know our trig. I know I do, but do you? The integral of cosine is sine. So the integral of 2 cos x is 2 sine x. So let's write that out. 2 sine x, where the upper limit is negative pi over 6 and the lower limit is negative pi over 4. The fundamental theorem of calculus says, let's write all that out. Positive 2 rather, sine negative pi over 6 minus, rewrite it, 2 sine negative pi over 4. All right. All right, this becomes, I think that's negative a half. I'll double check these at the end to make sure I'm all right. Minus 2, that's negative root 2 over 2. I do know that. So let me do that. Negative root 2 over 2. Let's see. We got a little bit of cancellations. Let me quick pause and make sure I did that right. I did it right. All right. So negative 2 or 2 times negative a half is 1. Negative 1. Ugh. Negative 1 minus negative root 2. And so I'll just put my answer up here as negative 1 plus root 2. So not pleasant. Not a pleasant answer at all, but, I hope it's right. I think it's right. So there you have it. Oh, right. We have to evaluate the integral between negative 1 and 1 of e to the stuff. Now, this is fundamental theorem of calculus, but what this also is u substitution. So what I'm going to do is I'm going to let u equal my 2 to the x minus 2. 2x minus 2. Because I can just take the integral of e to the u. It's just e to the u. Easy peasy lemon squeezy. Now what I have to do is I have to turn du and find du dx. So du dx is just going to be the derivative, which is 2. Multiply both sides by dx. So I get 2 dx, divide both sides by u, or 2, and du is equal to dx. Now I'm going to rewrite this guy knowing that you're going to become u and you're going to become du over 2. So I have the integral between, and let's just be specific, x equals negative 1, x equals 1, because the original problem has to do with x's with respect to x, of e to the u du over 2. I'll write this out as 1/2 and then do the same exact thing. Might seem a little, I don't know, a little much, but why not? Why the heck not? All right, so this is the same exact thing, just me taking that over 2 and ripping it out and making it a half. The integral is e to the u. So I have 1/2 e to the u, where my limits of integration are x equals 1 at top and x equals negative 1 on the bottom. U is 2x minus 2. So I'm going to rewrite this as 1/2 e to the 2x minus 2, where my limits of integration are 1 and negative 1. So I'm going to rewrite that and plug in 1. Let's get a different color here. 1/2 e to the 2 times 1 minus 2. It's going to make life easy. Minus 1/2, so same exact thing, but now plug in negative 1. 1/2 e to the 2 times negative 1 minus 2, close it. 1/2 times e to the 0, because 2 times 1 is 2, 2 minus 2, e to the 0 is 1/2 times 1. So I have 1/2, that's it, minus 2 times negative 1 is negative 4 when all this is said and done. So I have 1/2 e to the negative 4. So maybe what I'll do is I'll write this up here, way up here in a different color. We have 1/2 minus 1 over 2 e to the 4th. And that's my guy. Fun, 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 fun. Find the area under the curve over the given interval. So we have a graph of y equals 4x squared. Let's get a nice little visual. This isn't going to be a perfect picture. I have a hard time drawing graphs with this little pen thingy. But 4 over x squared looks, give or take, something like this. Give or take. Now what it's asking me to do is let's find the area under the curve between negative 2 and negative 1. It wants this area right here. Well, what's going to happen, and what I could use, is the integral of this equation is going to give me the area under the curve. I'm going to use -2 and -1 as my limits of integration to help me find this area. So this is going to give me some number, and that number is going to be the area under the curve, between the curve and the x-axis, between -2 and -1. So let's get rid of this mess. Let's start the problem from beginning to end. I need to find the integral of 4x, or rather 4 over x squared dx, where my limits are bottom limit -2 and -1, because my lower limit here is -2 and my upper limit's -1. Let's rewrite this. Let's bring that 4 out if you want to. Let's make this x to the -2 dx. Sloppy, but you'll get it. Let me see, 4 times, let's add 1 over -2 plus 1, x to the -2 plus 1, close that. My limits of integration are still -2, -1, can't ignore those. Can't ignore those. So we got 1 over -2 plus 1, which is 1 over -1, which is -1. And -1 times 4 is -4. X to the -2 plus 1, which is -1. Limits are -1 and -2. And let's just rewrite this out one more time before I use the fundamental theorem of calculus as -4 over x, limits being -1 and -2. So fundamental theorem of calculus says, once I have my integral complete, I rewrite my solution here, -4 over x, but instead of x, I am going to plug in my upper limit first, which is -1, close it, always the minus, rewrite that guy, -4 over x, but instead of x, plug in the lower limit, and do a little bit of math. -4 over -1 is +4, minus sign, -4 over -2 is going to be 2. 4 minus 2 is 2. So that little picture that I gave you, right, where we were focusing on what's happening here, and we had that little chunk, that chunk that's filled in right there has an area of 2, and that's how you find the area under a curve. Find the area between the curves, curve number 1, curve number 2. All right, so this is what I'm going to do. I'm just going to make believe that I know exactly what these curves look like. So that's a parabola. Parabolas usually look like U. This is a parabola. Parabolas usually look like U. Obviously, these aren't perfect. Okay, but what I also know is that x equals 1 when graphed is a vertical line. Okay, and x equals 3 when graphed is a vertical line. And I care about this shading right here in between these guys. So when you find the area of a curve in general, you take the integral. Now, if you have two curves, you're going to subtract one integral, or one equation minus another equation, integrate that, and then you have the area that you want. Now, the fun part about this is we know what my limits are. My limits are 1 and 3. So my job is to find this mess right here. So let me erase all of this, hit the reset button. Let's go for it. Now I'm going to write out this really big integral, okay, where I have, and you know what, let me put this whole thing in brackets, otherwise it's technically not, sound. 2x squared minus 8x plus 10 minus x squared over 2 minus 2x minus 1, close it, bracket it, dx. Now, if you're wondering, well, which equation is definitely the above one? My job is to find an area. It doesn't really matter which equation you put first, as long as you use common sense. If I do all of this and I get -50, that means I did it upside down, And I just changed my answer to positive 50 because you can't have negative 50 as an area. I'm not saying that that's what's going to happen here, but, we'll see. Now, what I do have going on in here, oh, by the way, I can't forget that I have limits, and my limits are 3 and 1. Ooh, 3 and 1. The Trinity. So I have, let me see. This is going to be a mess. Let's write this all out. Although I really don't need those parentheses anymore because I'm going to try to simplify parentheses. So I've got 2x squared minus 8x plus 10. Distribute this negative, and let me write it out as a better looking fraction. So that would be 1/2 x squared plus 2x plus 1. Close the bracket. Dx. I think I should be able to squeeze it in here. 3, 1. All right, 2x minus half an x is 3/2 x squared. 3/2 x squared. Can't forget that. I have negative 8x, positive 2x, negative 6x. 10 plus 1 is 11, last time I checked. Dx. Okay, so let's take the integral of each one. Let's take the integral of each one. I get 3/2, okay, times 1 over 2 plus 1, which is 3. How nice. X to the 2 plus 1, which is 3. Okay, let me put a huge brackets here. Minus 6. 1 over 1 plus 1, which is 2, x to the 1 plus 1, which is 2, plus 11, and you just attach an x. My limits of integration are going to be 3 and 1. So we get 3/2 times 1/3 is going to be 1/2 x cubed minus 3x squared plus 11x between 3 and 1. All right, now let's use the fundamental theorem of calculus, which has me writing this whole monster out, plugging in 3, minus sign, write this whole monster out, plugging in 1. So let's do it. So I have 1/2 times x to the 3rd, so 3 to the 3rd, this is going to be awful, minus 3 times 3 to the 2nd power, plus 11 times 3, minus, okay, the exact same thing, but plug in 1, 1/2, 1 to the 3rd, I can handle that one, minus 3 times 1 squared plus 11 times 1. All right, let's see what I can do in my head. Let's see what I can do in my head. I'm actually going to step to the side and just do all the math on a calculator and then come right back and tell you what the answer is. It's 11. All right, I ran out of room, so if I wanted to, I could have been like, all right, well, 27 over 2 minus 27 plus 33, and then have a big mess. But according to Mr. Calculator, I get 11, and I'm going to trust Mr. Calculator. Mr. Calculator, I'm sorry, or Ms. Calculator is pretty smart. So that's the area between curves. So whatever that black space was, that was right here. It's 11. And again, if I got negative 11, that's just because I had these upside down. I had the wrong order in which I had my lines. Not the end of the world. Just make it positive because you can't have a negative area. All right. Fun, fun. Find the volume of the solid that results when the region enclosed by the curves is revolved around the x-axis. All right, so what you have here is called the washer method. Just go with me here. Pretend that this little blue sliver is going to be spun around, or better yet, pretend that your finger is on this x-axis and you're slowly spinning this around. And when you spin this around, it creates like a kind of like a cone-shaped solid, almost like a bowl without a bottom. All right. Now what you have is a 3D figure created by this thing being spun around. That's what we're dealing with. Okay, this method is called washers. Now, there's another method called disks. It's on my YouTube. Look it up. But the washers method is called the washers method is when you spin it around the x-axis, there's this gap in between the actual curve and the x-axis. If there's no gap, if it's something that's attached to the x-axis, that's when you would use the disk. But this is called the washers because like a washer as a tool, you have that hole in the middle. So we'll have that. The way you do this is you set up an integral, right? You throw pi in front of it. You have an upper limit and you have a lower limit. And a lot of teachers use r to represent one of these. So you're going to have like both of your equations. I'm not going to figure out which equation is which. I'll explain that in a minute. But you're going to have like an upper equation, the equation that belongs on top, okay, of this solid. You're going to call that r sub o. And you're going to square it, and you're going to subtract r sub I, and you're going to square that, close that, dx. Now, again, when you are creating your integral, the r sub o is going to be the top part of the solid or the top part of the area. So this equation right here is going to be my r sub o, and this curve is going to be my r sub I. All right, so let's label what I know now, okay? And there's a few things that we have to do before we can even get started. First thing is I now know that this is going to be, this curve is my r sub I. So the parabola, which is this equation, is my r sub I. This is going to be my r sub o, so let's put that in our back pocket. What we also need is my upper limit and lower limit. Now, it might be obvious here, but what if it wasn't obvious? I have to find what x value this is, which is now called a, and I have to find out what this is b. Now, it looks like 2 and 0, and it probably is 2 and 0, but what if the numbers aren't as friendly? What if the equations aren't as friendly? What do I do then? Well, in order to find the x values that these guys intercept, I have to solve the system of equations. So just like you would do, like, you know, a regular system of equations, I'm going to use substitution. It's y equals this and y equals that. So set 2x plus 2 equal to x squared plus 2. Now I'm going to set this equal to 0 by subtracting 2x. Nothing combines over here. If I subtract 2, that makes my life a little bit easier because that all cancels out. And now I'm left with 0 equals x squared minus 2x. Okay, using the zero product property and a little bit of factoring, I get x times x minus 2. Set both of these equal to 0. And one of my limits, this guy is 0, so I guess I was right. And if I were to say x minus 2 equals 0 and add 2 to both sides, 2 would be my other limit. So now what I know is I know that my upper limit is going to be 2. My lower limit is going to be 0. My r sub 0 and r sub I is already set. Now we can get started. So let me erase this whole mess. I'm not going to clear the screen because I want to keep this stuff over here. Okay. All right. I'll probably have to write small because I have a feeling this is going to be a mess. So I've got 2 and 0. I've got r sub o, which I said is going to be my line. So I have 2x plus 2 squared minus x squared plus 2 squared, close it, dx. Okay, before I even think about integrating, I need to do a little bit of simplifying in here, so let me do just that. Okay, perfect square trinomial, so this part becomes 4x squared plus 8x plus 4 minus another perfect square trinomial. There's my phone. X to the 4th plus 4x x squared plus 4 blip, blip, dx. Let's combine like terms. Still not even close to being done yet. Not even close. I've got, what's it called? Distributing the negative. So I have 4, I can drop these parentheses, 4x squared plus 8x plus 4 minus x to the 4th minus 4x squared, which is good news. And you'll see why. And more good news. So I take it all back. This wasn't so bad at all. Minus 4, close it, dx. So you'll cancel out. You'll cancel out. And I'm left with 8x and negative 4x. So I have the integral between 0 and 2 of 8x minus x to the 4th dx. Once I integrate, that pi is just going to live right out there. All right. So I have the integral of 8x is going to be 4x squared. The integral of minus x to the 4th is going to be negative 1/5 x to the 5th. And my limits of integration are 0 and 2. All right, so let's leave this pi out here. Let's leave this pi out here. That pi is just going to exist out there, and I'm going to make sure that I keep it attached to my final answer. I hope I gave myself enough room. Fundamental theorem of calculus time, plug it in. So let's try to do as much in my head as I can. I have that pi there. I'm going to plug in 2. So I'm going to have 4 times 2 squared, which is 4 times 4 is 16, minus 1/5 times 2 to the 5th power, which is 32. So 32 over 5. I'll deal with that when I have to deal with that. Minus pi. 0. Oh, look at that. Look at that. If I plug in 0, I get 0 minus 0, which becomes 0, which makes all that 0. So I'll just completely erase you to make my life a little bit easier. 16 minus 32 over 5. Ugh. I'll consult Siri. 16 minus 32 fifths.
The answer is 9.6.
So this final guy is going to be, what the heck? This final guy is going to be 9.6 pi. So yeah, that's the washer method. Very similar to the disk method. Again, this is the washer method because when you spin it around, you get that space in between, unlike the disk. I have a video on that. Go find it. It'll be great for you. Find the volume of the solid that results when the region enclosed by the curves is revolved around the x-axis. All right, so basically what we're doing is we're taking this little circular looking thing right here, and we're pretending that that's like like a piece of paper, like a 3D printer thing, and we're spinning it around. So what's going to happen is this little orb right here is going to spin around and create a 3D orb looking thing. All right. This method is called disks. Now there's another method very, very, very similar called washers that we're not going to use here. Washers is if you kind of have like a space, like when you spin it, you create like a donut or a space in between. It's called washers because just like the tool washers, it has a hole in the middle. Not this. This is called disks because you're going to spin it around and not have any space in between it. Now, what we're going to do is we are going to take the integral of whatever equation this is. So we'll call it r. We're going to take the integral of r, square it. We're going to have a lower limit and an upper limit, and we're going to throw pi in front of it. Now, if you're looking at this and saying, that's kind of like the volume of a cylinder, you're absolutely right. Because what we're doing is we're kind of creating like a continuously changing cylinder, if that makes any sense at all. Okay, so this is the method that we're going to use. Now, we have our r. That's our r. And if you're like, what about y equals 0? Y equals 0 is just a fancy term for the x-axis. Don't worry about it. Don't worry about it at all. Now, what we don't have yet is we don't have our limits of integration. We don't have a and b. So this is what we're going to do. We have to find where our curve, where r crosses the x-axis. In other words, where is negative x squared plus 1 equal to 0? Now, we can look at this and say, well, I think it's kind of obvious what the answer is, but you can never be too sure, ever. So since I'm not too sure, and since these numbers could be not friendly in the future, I'm just going to do it this way anyway. So I'm going to add x squared to both sides, like that. I'm going to square root both sides. Don't forget your plus or negative. And that gives me x is equal to positive or negative 1. So my limits of integration are positive 1 and negative 1. All right, so now I know what I have. I think if I do all of this here, that leaves me with enough room. So let's see if I can pull this off. I have pi times my upper limit, which is going to be positive 1, my lower limit, which is going to be negative 1, my equation, which is going to be negative x squared plus 1, all of that squared dx. Before I can even begin, I need to square that guy. So this is not as simple as squaring both numbers. This is a perfect square trinomial. So this gives me x to the fourth, negative 2x squared, right? And positive 1. Now I integrate. Pi comes along for the ride. This gives me 1/5 x to the fifth. This gives me negative 2/3 x to the third plus x. My limits are negative 1 and 1. All right, so I'm going to now use the fundamental theorem of calculus. I'm starting to get a little nervous that I don't have enough room, but we'll find out. I'll just write small. Fundamental theorem of calculus says rewrite this guy, but replace every x with the other limit. So I have pi. Let's do a little bit of mental math. 1/5, because the numbers aren't that bad. 1/5 times 1 to the fifth is 1, so 1/5 times 1, easy. Minus 2/3. 1 to the third is 1, so minus 2/3 times 1 is minus 2/3, plus x, which is plus 1. Okay, got it. Minus. The second part of fundamental theorem of calculus is write that out again using the lower limit. So I have 1/5 times x to the fifth, which is negative 1/5. Same thing's going to happen here, but that's going to be positive 2/3 minus 1. If you're looking at that, you're like, oh, well, this is the exact same. After I distribute the negative, this is the same as that. That makes sense because these guys are symmetrical perfectly. So I'm not going to lie. I'm just going to quick use Siri and find out what 1/5 minus 2/3 plus 1 is.
It's approximately 0.5333.
So 0.533, I'll leave it like that. That's no problem. 0.5333 pi plus 0.5333 pi is going to end up being 1.0666 pi. And that's the discs method. Fun, 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 fun. Find the volume of the solid that results when the region enclosed by the curves is revolved around the y equals -1 axis. All right, so what this looks like is a washer's problem. And what we're usually used to in a more basic, even though it's difficult, version is you're used to spinning it around the x-axis. Well, this is different. So when it was spinning it around the x-axis and you use the washers, you have your lower limit, you have your upper limit. You throw a pi there, okay? And when it's washers, you take what you determine to be like the upper curve, which is RO, which this is the case, and we have RI here. What you did back then is you would say RO squared minus RI squared dx. Well, when it was the x-axis, y is 0. So that was fine. But now that we're spinning it around a different axis, we have to change things up a little bit. So let's erase some of this because we are adding another unit when we spin it around. If we were to spin it around the x-axis, no big deal. But now when we spin this around, we have to pretend that this guy is creating like this weird donut-looking shape thing here. I can't draw. But it kind of creates a bowl where actually you have to believe that there's like a hole in the middle. So we kind of have this weird looking donut-y thing. Okay, but we're adding another unit. So whatever number y is, the best way to probably view this is minus y. Okay, where in this case, y is -1, so it'll become +1, but then you take that, you square it, and then you subtract r sub I, do the same exact thing, square that, close it, dx it. So that's what we're looking at. Now, the other thing that we have to take care of is even though it's kind of obvious, we can never have the benefit of the doubt and say that that's definitely 0 and that's definitely 1. So we need to find out what my upper limit B and my lower limit A is. So I'm going to do that by finding out where these two guys intersect. So we're going to pretend that that's a system of equations, and we can solve that using substitution and say root x plus 1 equals x squared plus 1, bada bing. Let's set this equal to 0. So let's subtract root x. Let's subtract 1. Let's subtract root x. Let's subtract 1. That goes away, and you have 0 equals x squared minus root x. Okay? The way I'm going to handle this is I'm going to use zero product property, and this is going to be strange, but go with me here. I'm going to factor out a root x. By factoring out a root x, I am left with a root x cubed, or x to the 3 halves, minus 1. And we could use the zero product property. Root x is equal to 0. So this factor equals 0. Square both sides. X is still equal to 0. So that gives me that guy. My lower limit is kind of obvious. My upper limit should be 1, but just to be on the safe side. Square root of x cubed minus 1 equals 0, add 1, square root of x cubed equals 0. Square and cube root both sides, x is equal to 1. I'm sorry, 1. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. I'm getting too jumpy here. Getting too jumpy. All right, so now what I have is I have my upper limit, I have my lower limit. Time to have some fun. Let's call U1, let's call U0, and let's write small. See what happens. Let's get rid of all of you. If you have to, clear that out, clear that out. All right. Pi, integral, upper limit, lower limit, bracket, r sub o I called the square root. So I'll call you r sub o, I'll call you r sub I. So this is going to become r sub o, which I don't know why I did that. R sub o is root x. So I'll write that as x to the 1/2. Makes sense to me. Plus 1 minus -1, so plus 1 again, squared, minus r sub 2, or r sub I, minus r sub I, which is going to be x squared plus 1 minus y, which is -1, so plus 1 again, squared, bracket it, dx it. Okay, so let's do a little bit of simplifying. Pi still lives there. I'm far from integrating. So if I were to do that, that becomes x to the 1/2 plus 2 squared minus x squared plus 2 squared dx. Okay, let's do, we've got ourselves two perfect square trinomials that we're going to end up with. So this is going to become x plus 4x to the 1/2 plus 4 minus, this is going to become x to the 4th minus, or rather plus 4x squared plus 4, close it, bracket it, dx it. Okay, let's try to simplify and distribute the negative at the same time. This is going to be interesting. So x isn't going to be touching anything else, so x is just x. Plus 4x to the 1/2, that's not going to be changing anything either, so plus 4x to the 1/2. Plus 4 and minus 4 will cancel out. We've got minus x to the 4th minus 4x squared. That's our integral. There you have it. So I'm going to leave that down there. And I'm going to do the integration up here after I erase everything. This is going to be a mess. However, the nice thing about this problem is since the lower limit's 0, things will go away, and that's going to make our lives a whole lot easier. Okay? All right. Pi still lives out there. The integral of x is 1/2 an x squared. Okay. The integral, this is going to be an interesting one, of 4x to the 1/2. The 4 is going to live there. And then you get 1 over 1/2 plus 1, which is 3/2. So 1 over 3/2, right? And I'm just going to do the math right here and then erase things. 1 over 3/2, when you divide by a fraction, you just get its reciprocal. When you divide 1 by a fraction, you get its reciprocal. So 1 divided by 3/2 is 2/3. And you end up with 8 over 3. X to the 3/2. Okay. Minus 1/5 x to the 5th minus 4/3 x to the 3rd. My limits are 1 and 0. All right. Pi 1/2 x to the 2nd power is now 1 to the 2nd power. So you tell you what, let's make life easier. If we're doing the fundamental theorem of calculus, 1/2 times 1 squared is just 1/2. Let's not overthink it. Plus 8/3 plus 1, or times 1 rather, so plus 8/3 minus 1/5 times 1 minus 4/3 times 1. That guy's done. Minus pi. And I'm going to plug in 0 for all of these. So 0 times stuff, who cares? 0 times stuff, who cares? 0 times stuff, who cares? 0 times, they're all going to become 0. So this ends up being pi times whatever this guy is. I'm just going to let Siri do it. 1/2 plus 8/3 minus 1/5 minus 4/3.
It's approximately 1.6333.
I'll take that. 1.6333 times pi is going to be 1.6333 pi. So that is the volume of a washer bowl thingy spun around an axis that is not the x-axis. Very tricky problem. Tons of fun though. Use the method of cylindrical shells, or just regular shells, to find the volume of the solid that results when the region enclosed by the curves is revolved about the y-axis. All right. So we've got ourselves this shape-looking thing created by that line, that curve, enclosed off by 0 and 4. And what we're going to do is we're going to rotate this around the y-axis to create some kind of weird 3D top-looking shape that looks like something like that. So as you can see, I'm not a gifted artist, but that's basically what we're getting here. Now, generally speaking, when you use the shells method, all right, when you use the shells method, the way you find the volume is you take the integral where your limits of integration are going to be between a and b, which is created by 0 and 4. So 0 and 4. You multiply, or you take the derivative, the integral of 2 pi x, and then you take whatever this shape is, f of x, whatever curve this is. However, in this case, we have to mix in a little bit of washer type knowledge, where instead of just me taking a regular old picture and spinning it around, I have like an upper line, which I'll call RO, and a lower line, which I'll call RI, and we're going to find out what RO minus RI is, and then dx. Okay, so that's what we're dealing with here. All right, so our OR is 7. Our OI is root x. This lower limit is A. This limit is B. And we have all the information that we need to get started. So let's get started. We have, I'm sorry, I'm getting a pen. We have, let's move 2 and pi out here. Keep x right there. Lower limit's 0, upper limit's 4. Parentheses RO, my upper guy is y equals 7, so we'll just do 7 minus RI is root x, close it, dx it. Okay, so this becomes 2 pi. Distributive property says 7x. Well, I still have my integral. I can't get rid of that. Not yet. 7x minus, now this is x to the first times x to the 1/2, so we'll turn that into x to the 3/2 dx. Now let's integrate that. 2 pi comes along for the ride. The integral of 7x is going to be 7 over 2x squared minus the integral. Now remember when we do this, so we'll just kind of pull this aside. We're going to have 1 over 3/2 plus 1 x to the 3/2 plus 1, right? So this will become 1 over 5/2. 1 divided by a fraction is reciprocal. So 1 over 5/2 is 2/5 x to the 5/2. Look at me just barely fitting that in there. My limits of integration are still 0 and 4. But I have what I need to start using the fundamental theorem of calculus, so I'm going to do just that. I'm going to do just that. I'm going to write this out, plug in 4 for every x, so 2 pi 7/2 4 squared minus 2/5 4 to the 3/2, close it, just making sure I didn't miss anything, minus that guy, plug in 0. Now let's use common sense here. 2 pi times 0 minus 0 is going to be 0, so that whole thing will become 0. Let's just get rid of it. So let's do a little bit of simplifying. All right, you can use a calculator if you want to, but I don't have one on me right now. So we've got 2 pi. 4 squared is 16. 7/2 times 16 is going to be 56. So 56 minus, I guess I forgot that guy right there, 2/5 times 4 to the 3 halves. I am going to use Siri for that one. Or is it 5 halves? 4 to the 5 halves. Yeah, it's 5 halves. What's 4 to the 5 halves power?
The answer is 32.
Okay. What's 2/5 of 32?
The answer is 12.8.
So this becomes 12.8. What is 56 minus 12.8?
The answer is 43.2.
And what's 2 pi times 43.2?
It's approximately 271.4336.
Okay. So that's shells for you. Not as crazy as some of the other things that we've done that look like discs and washers and stuff like that, but, also not a ton of fun either. So unless I personally find it great. It's great. So thank you. Thanks for watching. Thanks for loving this stuff. Find the volume. The base of a solid in this is the region enclosed by the semicircle y equals square root of 25 minus x squared, and the x-axis. Cross sections perpendicular to the x-axis are squares, so that's important. Cross sections are squares. So this is me attempting to draw a square using this pen thingy that I'm using. It's never a good idea. So when you imagine what's going on here, a cross section is a slice, and you're cutting this down. Okay. Now, if I were to cut this solid, this volume, and literally cut it in half so that I'm looking at almost a half of a globe, what I'm looking at are squares with lengths of side lengths of 25 minus x squared and root 25 minus x squared. Now, when you're solving one of these problems, right, the volume of one of these problems is found by taking the integral of the upper limit, lower limit of the area of this particular shape. So we'll say that's called a of x dx. Now, the area for this particular shape is going to be a side squared, so the square root of 25 minus x squared, which makes life really easy because, a square and a square root cancel each other out, giving us just that right there. So what I'll do is I don't need this picture anymore. That picture's now gone now that I have my area formula. I can find the volume by taking the integral of 25 minus x squared dx. Now, what's my limits of integration? Well, if this is the formula of a circle, that tells me that this guy right there is going to be my radius squared. So in order to find the radius, I take the square root of that, which is 5. And we can see right here, if this is a circle, it goes out to 5, it goes out to -5. So this is going to be my upper limit. This is going to be my lower limit, 5 and -5. So let's do all of this. Let's get rid of you. Let's get rid of you. The integral of 25 is 25x. Can handle that one. Minus the integral of x squared is 1/3 x cubed. And my limits were 5 and -5. So now it's time for the fundamental theorem of calculus. I'm going to rewrite this guy, plug in 5, hit the minus button, rewrite that guy, plug in -5. So I have 25 times regular 5 minus 1/3 times 5 cubed, which is going to be 125. Close that. Minus 25 times -5 minus 1/3. It's supposed to be 25 times -5. Let me clean that up. Let me sneak that in there. 25, I think I said it, I just didn't write it, times -5 minus a third of negative 5 cubed, which is negative 125. So we should know that since this guy is a perfectly symmetrical shape, that whatever number this is, once I minus this guy, it's going to be the opposite. So it's that guy plus the same exact number. So what is it? What's a third of 125? Let's ask Siri. What's a third of 125?
It's approximately 41.6666.
All right, so 125 minus 41.666.
It's 83.334.
So this is going to be 83.333 minus negative 83.333. And what is 83.333 times 2?
It's 166.666.
I don't like that. But that's the answer that we have. So the volume, according to this information right here, which is found by basically taking the area of a square, making life easy for us, is 166.6 repeating. All right, there you have it. A particle moves along a horizontal line where its velocity is given by the function below. So there you have it. Find the distance and the displacement over the interval. All right, let's understand the difference between the two. All right, displacement is the idea that we start somewhere, and let's just say I take 5 steps forward, I take 8 steps backwards. My displacement has me at -3 steps. What does that even mean? That means from where I started to where I'm finished, I am 3 steps backwards. Now, if I were to look at the same exact problem, the same exact scenario as far as distance goes, where I take 5 steps forward and 8 steps back, I don't care about like a negative position. I'm taking 13 total steps. So what we're going to do is we are going to find displacement. We're going to find distance. One's going to tell us where we are currently at the moment, and the other one's going to tell us where or how many spaces, units, whatever that we moved. So let's start with the easier one first. Let's start with displacement. Okay. Displacement is pretty simple, relatively speaking. You take the integral from where you start to where you finish of your velocity function, and that's pretty much it. Okay, nothing fancy, nothing crazy. That is the displacement. So my velocity function was 3t squared minus 22t, close that, dt. The derivative, the integral of 3t squared is t cubed minus 22t, the integral of that is 11t squared, and my limits of integration are 0 and 10. Fundamental theorem of calculus says that we write this guy out, plug in 10, so we have 10 cubed, which is 1,000, a k, if you will, and 11 times 100, which is 1,100, minus, notice I didn't write it out, plug in 0 cubed, get nothing. Plug in 0 squared, get nothing. So nothing. So we end up with negative 100, whatever. What are we talking about? Units? Nothing. It doesn't say. So we'll say that our displacement is 100 units backwards. So this is not too different from any other regular problem so far that we're used to seeing. That changes though, because if you're trying to find the distance, you don't care where you end up. You care what you've done in the positives and in the negatives. So what we do here is we set up an integral between 0 to 10 of the absolute value of our vertical or our velocity function. Okay, so that requires us doing a few things. Noticing I'm writing small because this takes a little bit of space for me. All right, so the first thing I have to do is I have to find kind of what's critical points. If I'm going to be going forwards, that tells me a distance of something. And if I'm going backwards, that tells me a distance of something too. So what I kind of need to do is find out when I'm going forward and when I'm going backwards. And the way I can find that is I find out when velocity is increasing and when velocity is decreasing. So here's my velocity function. Let's set it equal to 0 a la critical points. A la critical points. Let's factor out a t. So now we have t times 3t minus 22. According to the zero product property, t is 0. So that's one of my times. So right at the very beginning. So that makes life kind of easy. If I add 22 and divide by 3, that gives me 22 over 3 for where things change. Okay, so I'm going to create kind of like a sign chart. 22 over 3 is where the magic happens. I'm going to plug in, normally I would plug in 0, but I can't plug in 0 because technically that's a critical point. So if I plug in 1 and find out if this gives me positive or negative, that'll help. And if I plug in 10, I can actually do 10. That'll help me determine if it's increasing or decreasing. So plugging in 1 and doing some mental math, I get 3 times 1 squared minus 22 times 1 gives me a negative number. So I'm decreasing here. So between 0 seconds and 22 over 3, that's supposed to say 3. I don't know why that looked like 13. Between 0 and 22 over 3, I have, or I'm going backwards because my velocity is negative. Can I erase that little one-looking thing? I'm scared, I'm scared, I'm scared, I'm scared, I'm scared. Let's go. Where? Come on. Go away. Yeah. All right. Now let's see what happens when I plug in 10, because I'm allowed to plug in 10. See what kind of number I get. 300 minus 220, positive, increasing. All right. Let's cut this down a little bit more. So in my negative section, all right, I'm going to set up an integral where I'm negative from 0 to 22 over 3, so 0 to 22 over 3 of negative VT. So by throwing a negative in front of this formula, I am allowing myself to kind of say, all right, well, I'm going to get a negative distance, but by negativing, you know, a negative, it becomes positive. So that'll be helpful. My other inequality, which shouldn't take up too much space, is going to be from 22 thirds to 10 of regular velocity. Nothing fancy about that, dt. All right? So I'm going to have the integral between 0 and 22 over 3. Let's throw the negative out here. Of Vt is 3t squared minus 22t dt. I already know what's going to happen. I'm going to end up with this guy, so I have t negative t cubed plus 11t squared between 22 over 3 and 0. So when I do the math here, when I do, the fundamental theorem of calculus, I get negative 22 thirds cubed, whatever that is, plus 11 times 22 thirds squared, minus zeros. So 22 over 3 cubed.
It's approximately 0.
That's not at all what I wanted. What's 22 divided by 3?
It's approximately 7.333.
What's 7.333 cubed?
It's approximately 394.3165.
394.316. So we'll put 32 plus. What's 22 over 3
It's approximately 7.
What's 7.333 squared?
It's approximately 53.77.
What's 53.772889 to the times 11?
It's approximately 591.5017.
Okay, that actually did work. So 59.1. 591.5 minus 314.32.
It's 277.18.
Okay. Lots of calculating there. This guy's going to be slightly more challenging. Let's get a fun color. As you can see, the fun color is popped off to the side. Let's get a nice little orange in there. All right, so we already know what happens when I take the integral of vt because that happened over here. So I have t to the third minus 11t squared. Limits are 10 and 22 over 3. All right, so the nice thing about this guy right here is I know what's going to happen because I plugged 10 in over here and got negative 100. Now, when I plugged in negative 200, or when I plugged in, 22 over 3 into the negative form of this, I got positive that. So I would get minus 277.18 for this one, which is a double negative becomes a positive 177.18. So my final distance traveled is found by me taking u and adding them together, 177.18 plus 277.18.
It's 454.36.
And that's your guy. And that's distance and displacement. So on a fun scale, I'd say it's about an 11 out of 10. On a difficulty scale, same. But it's not work if you're having a great time. Am I right? Like and subscribe. Thanks for watching.